We're so happy that you can join us here today at the 6th MOC Alliance Workshop. We had a big break with our COVID hiatus, so we last met here back in March of 2020 before the world stopped on us. So it's nice for us all to be able to come together again. My name is Nancy Clinton. I'm the Managing Director of the MOC Alliance, and I'm really happy to join all of you. We have a very exciting and full agenda for you here today, and we look forward to sharing what's been going on at the MOC. On your tables, you'll see a QR code. That QR code will lead to a schedule of events throughout the day for all of you to see, and it will explain some of the presentations and give background to the presentation. Comprised of 5 different academic institutions, we're very excited that Boston University is the host of the MOC Alliance. We're very thankful to have the longtime support of Boston University leadership, particularly that of our Vice President and Associate Provost of Research, Gloria Waters. We're delighted to welcome Dr. Waters to start us off today with a warm welcome from Boston University. Gloria?
Very much, Nancy. So, as Nancy said, we're really delighted to be back here in person for the MOC Workshop. And this is an annual event, and we're hoping we're going to continue to meet like this for many years to come. So, the idea of an open cloud was originally conceptualized 9 years ago. Amazing. And the project has really exceeded all of our expectations. We now have production cloud services offered that are operated by university research IT groups that support main researchers from many different universities, and also a robust systems research community studying the behavior of the cloud. So, as the VP for Research at EU, who's been involved in this pretty much since its inception, I really appreciate how the Alliance is presenting opportunities to enable computer systems researchers to engage with industry, and also the open source community to work on important problems and to provide a unique, cost-effective resource that is really helping a range of computational-driven domain research across all of our universities. The cloud is truly becoming a new library where data is discovered and the new lab where science is done. And it's really exciting to see the MOC Cloud Alliance helping to define the future of something that's really impacting so much of academic research. We're really looking forward to seeing the proposed iScale NSF Center expand in this successful model of industry research collaboration. And I'm really happy to welcome all the companies that are attending the workshop today. It's very exciting to see the diversity of companies that are represented here today, from cloud providers to major banks to software developers and to computer chip manufacturers. None of this would be possible without the collaboration of the region's research institutions, our industry partners, the MJPCC, and the support at that very critical junctures of the MassTech Collaborative. The support from an institutional level and the involvement of research IT partners across the partner universities has really enabled our researchers to flourish. At BU, Wayne Gilmore and Tracy Schroeder, and at Harvard, Scott Yoko and Clara Zelmakova are really playing a key role in driving the production cloud services and also engaging the research IT services from all the other institutions in this really important effort. One particularly innovative partnership that I'd like to highlight is that with Red Hat and the Red Hat Collaboratory. And this is really a key aspect of the MOC Cloud. The Collaboratory has really allowed the involvement of Red Hat engineers and faculty and student researchers. And in the past 2 years, 35 different research projects have been funded in areas that go from machine learning and automation, operating systems, big data platforms, and also AI. So the benefits of the Alliance continue to extend well beyond technology. The MOC Cloud has provided all of our participating institutions with a really unique opportunity to explore a different and also very productive way of engaging with industry in ways that are really beneficial both to industry and to us. It's provided our academic departments with an opportunity to develop courses they need students in collaboration with industry, which is really critical to our students. And it's also provided our IT departments with an opportunity to experiment with new models for supporting research computing and new approaches to connecting their respective research infrastructures. And I think most importantly, it's also allowed us to really experiment with future public-private partnerships that can be pursued in an industry and a university setting. And I think most importantly, it's really validated our initial vision of the MGPCC as really a shared infrastructure where the whole is greater than the sum of the parts. The MGPCC has been really critical to all of this. So I'd just like to thank our academic partners who are Harvard, MIT, Northeastern, UMass, Boston Children's Hospital, and then also the MGPCC. Our core partners who really commit valuable resources and technical and business expertise, those being Red Hat and Two Sigma, and also our contributing partners who donated hardware and software, and they work with Mass Open Cloud on really exciting projects that they bring a lot of critical technical expertise to the table. So Wayfair, Cisco, Intel, NetApp, and AMD. We also really want to thank the Commonwealth of Massachusetts and in particular the Mass Tech Collaborative. They really helped drive this vision into reality from day one, and they provided critical seed funding and also continuous guidance along the way. We want to thank all of you, the MOC community, because there's really contributions that are made from industry, students, researchers, and many others that are really helping to allow the MOC Alliance to really flourish. And this is really important to the effort. And I would say that a very complex collaboration like this really needs a lot of coordination, organization, legal support, and all of those things that an institution can provide. And Viva is really thrilled to continue to support this multi-institutional project. And we're really pleased with how successful the effort has been to date. Finally, I want to thank the Brewery Institute for Computing, which has really incubated the MOC from its inception. You established the brewery to really take on these leading-edge, high-risk ideas and projects, to incubate them, and then navigate all the legal and administrative hurdles in this realm of rapidly evolving technology in analytics and computing. It's done just a masterful job, I think, with the Mass Open Cloud. So really a lot of thanks to its director, Ignace Pascalides, and also to Stephen Brown, who's the director of finance and administration, who's been incredibly supportive of all of the efforts of the Mass Open Cloud. So overall, I'd say watching the development of the Mass Open Cloud has been really inspiring, and it's been an enlightening experience. It's really provided us with a great model of how we can collaborate with industry and the importance of these public-private partnerships that involve states, involve companies, involve many different universities. I think it's really clear that the Mass Open Cloud Organization is really making significant contributions to the world of cloud computing, and I'm quite confident that its successes will continue on and have a lasting impact for years to come. So thank you very much, and I hope to have an enjoyable and productive workshop. Thank you.
All right, welcome everybody. It's so great to see all these faces again. It's been a couple of years. So Peter and I decided to sort of combine our session together. I tried to, I don't think this is totally up to date, so please don't be insulted. These are actually the people that have made substantial contributions over the years to the project. It's sort of mind-blowing to me a little bit. And I'm sure I missed a lot of them. So the place that Gloria said, I think is perfect, is that cloud systems are so central to research today. It's the library, it's the laboratory where research is done. And those are like the build systems. It's actually fundamentally changed how we innovate. It's allowed us to actually deploy services, be informed by real usage of what's going on, incrementally deploy and evolve services with real users, do it at scale. It's changed the pace of how fast systems evolve. But its challenges, and this is why we were able to do this is both for users, it lacks facilitators that need support platforms and community. It's expenses for the public cloud is unpredictable, and everyone is trying to lock you into their public cloud. And then for us as systems researchers, or those of us that are in that part of the community, you don't have visibility if you're not in a public cloud benefit of the real usage. The innovation is very difficult to do unless you go for sabbatical to AWS or Google or Microsoft. And even for them, it's important that this innovation be done by the broad community. So we had this crazy vision in 2013 that to just build our own cloud. You know, the MGPCC was there, and this was an opportunity. And we wanted it not to just be a production cloud, not to just be a place to host real users, but also something that then informed the systems research and the evolution of technology and engage industry and open source to kind of close that loop. So in other words, do what's happening in this rapid evolution of systems research and hyperscalers, but do it for all academia, the open source community, and industry, and do that sort of make it open cloud. So that was kind of a crazy dream. And so we've already said Riri was supporting high-risk things. It really was high risk when we started this thing. Kind of shockingly, it sort of worked. We have now a whole series of projects that are production cloud offerings. They're stood by people that really know how to operate things at scale. We have projects that are engaging researchers, and enabling research, and then helping the research transition to open source, which can then impact products. So that whole cycle, there's kind of key efforts that have evolved for all of us. And where it's gone to now, though, is that we no longer just do this as kind of an ad hoc way of doing the MOC. There's now responsibilities to the university for these production services, etc. So we've kind of built the whole structure around that, of governance. And you're going to hear about sort of some of these production aspects from others. Critical from my perspective is that one of our goals has always been to actually close the loop and make this a real cloud. We're charging people for the use of it. Yes, rates that are more travel massive, pretty class, but we can now get to. So that allows this whole initiative to grow to the scale it can get to because of the MGHPCC and the incredible innovation of the system community. There's a user base that are actually using this and being charged from it. And we're just on the point of about to start doing it. Right, Scott? Excellent. So, you know, what's that? Am I making it? Okay. Wow. I never get told people can't hear me. All right, so you're going to hear talks about all these different efforts and how this cloud's becoming real, not anymore sort of this endeavor. But the part that I kind of came into this as well, we could stand up cloud. Our goal is to do research, it's to do innovation, and establish the connections that we sort of talked about at the beginning. So in this the rest of the presentation, we're just going to focus on how the Alliance has succeeded on having research informed by the promise of real cloud, impacting open source, resulting in products that then actually come back and impact the cloud. And all these projects that I'm going to allude to are either in birds with feathers. There's a lot more, but this is the subset of things that are presenting talks or presenting birds with feathers session, or that are actually poster sessions. So orange projects are large projects which are affiliated with the Mass Open Cloud. Red are research efforts that have gone on. Green are things that, or partially green are things that are already having an impact. So to start off with the MGHPCC, that'll be the next major talk. That's an industry consortium where it's multiple universities in the same massive scale data center. That's just an incredible opportunity for us to create a collaboration like this. None of this would be possible without that. We decided to kick off the Mass Open Cloud back in 2013. It was supported by the Commonwealth, a set of core partners that helped us kick it off. And fairly soon, within a couple of years, Red Hat decided to create its first real research endeavor, Red Hat Research and then the Red Hat Collaboratory, which is this very important connection to support a lot of the systems research that we're going to talk about here. So one of the first challenges we had was we addition our hardware. We want to do staging and production and different services. We also wanted to find a way to share hardware with other projects. I still remember early on talking to one of the major HPC clusters and sort of saying, well, can we share hardware? And they said, why would we share hardware with you? We run our hardware at 99% utilization. It's an HPC effort at a certain tier 2 site. They said, yeah, well, we're cloud. We run our hardware at probably 30% utilization most of the time, and occasionally go on 150%. What if I give you 100 servers 9 days out of 10, and I ask for 10 servers on the 10th day? And they said, oh yeah, we'd love to share with you. You're an idiot. We'd love to share with you. So we wanted to come up with a mechanism to let us move, computers between different clusters. Everyone's a silo today. And we also wanted to support efforts like Jonathan Papu's research on bare metal operating systems and Unicode, where you want full control all the way down. So one of the first research projects we built was called the hardware isolation layer. Gave us that capability to slide in under any cluster without really affecting it. And that was very powerful. We ended up using it in production on the MOC. In fact, we've been using it until very recently. But we started hitting the need to make things rapid, to be able to move computers quickly between them. Copying your disk into a local disk turned out to be really problematic because you had to start over again when you were decommissioning that server and moving to a different cluster. And security was becoming a concern. The CRIS project for Boston Children's Hospital, at the time we were not doing anything that was compliant, but we were realizing we were going to have to start at some point dealing with HIPAA regulations, things like that. So, so that ended up kicking off a major collaboration, Two Sigma, Red Hat, the US Air Force, MIT Lincoln Labs, and a series of capabilities got built. The bare metal imaging service that was disaggregated storage, Keyline that did attestation that measured that the computer wasn't compromised by the previous user, and Linux Boot, where we actually burned this into some of our servers, which was secure firmware. Actually, as a result of this, the Keyline has become a, so Keyline has actually become a broad open source community, going from sort of an unknown thing, and it's actually used in IBM's public cloud today. That's right, Jim, isn't it? Yeah, okay. So it's actually used in the public cloud, affecting the product at large scale. And what we wanted to do was make the whole thing kind of at that same level. So we worked together with Red Hat. We incorporated components from Neutron and Ironic from Open Compute. And then we actually have a production version of it, which is got a broad open source community behind it, rich support for networking, a wide variety of servers, valid test code. And this is actually now being rolled out in production in GHPCC. We're trying it now with a whole bunch of different clusters. And it's really exciting to see something come that entire arc now becoming a critical component for the latest boot hardware. And it's actually resulted in more research. So marketplace-based CSI is providing an incentive mechanism. So not only do you give them servers when you're not using them, but you have an incentive if somebody else really needs it to actually go and offer your services into the marketplace. One of the key things having a production capability allowed us to do was go after creating a new test bed. The Open Cloud test bed, which Mike Zink will talk about in a bit. That's a, oh, I'm sorry. I was going to hand over to you.
Peter Dismeyers. I've been working on this with Iran for close to a decade now. So, yeah, I wanted to talk about some of the, especially some of the storage-related aspects of the work that's going to be covered later today. So, in particular, the ESI work, which really has been Iran's baby, has enabled a number of things, and a key one that's brought some of you here today is that the NSF Open Cloud Test Bed is a community infrastructure grant, and it's a form of bare metal cloud. It's an extension to the existing Cloud Lab test bed. It's part of the NSF's test bed program for supporting systems researchers who develop operating systems, hypervisors, and other components of the cloud. So there's two key parts of the OCT. There's accelerator enablement and elastic hardware access. So accelerator enablement draws on the depth of experience with programming hardware at universities that you'll see in more detail in tomorrow's program, actually. Supporting use of high-performance network-attached FPGA accelerators by researchers software and tool chain support. But the thing that makes OCT different from all the other NSF testbeds is its use of ESI, which essentially allows a bring your own device model for cloud testbed. So the reason that's important is, as a university researcher, I have access to a lot of computing resources that are provided by my university. These are both purchased from institutional funds and also, buy-in programs where, each individual grant will buy some amount of computing and donate it to a shared pool. So I've got, except that I can't use those because I'm a systems researcher. And the first thing I need to do usually is to reinstall the operating system and, make all sorts of, basically, the people running these high performance clusters are not going to let me do this sort of thing to any of their machines. So the NSF has been addressing the need for systems for this type of research by funding the Cloud Lab and Chameleon testbeds. But ESI offers us another way forward where these can be virtual testbeds. We've worked with the university research IT departments, especially Wayne Gilmore, BU, and Scott Yokel at Harvard, so that Open Cloud Testbed can use ESI to borrow machines from the research computing clusters to use them in the Open Cloud Testbed for the duration of an experiment, and then securely return back when we're done. And this sharing gives us, the efficiency, the statistical multiplexing that Ron was talking about, especially because most of the researchers using Cloud Lab actually try to submit to the same set of conferences with the same deadlines. And so if you get to the week before the OSDI deadline, the machines are going to be booked solid. For weeks afterwards, there's probably a lot of idle time. By sharing with ESI in the Open Cloud Testbed, we're going to be able to share computer use across a diverse range of researchers. Don't all use the machines all at the same time, so that we can borrow extra machines in time of heavy load, and then in turn we can provide our idle machines at other times when they're not being used. So one of the interesting things we learned, so back to the Mass Open Cloud in general, one of the interesting things we learned running a production cloud was how to run SEP. So sometimes we learned how not to run it. There was the great storage disaster of 2017 when we lost 300 or 400 terabytes of data. But anyway, our SEP experience, learning how to use it, led to the Northeast Storage Exchange project, NESI. It was launched with NSF funding, and it's been sustained since then by researcher buy-ins. It provides file and object services to the NVHPCC community on a 50 petabyte hard drive-based SEP pool, and in addition, a 133 petabyte tape library. Now, as researchers, we spent a lot of time, Ron and I especially spent a lot of time looking at object storage on SEP. So that's a widely recommended architecture for data lakes, for these shared storage tools that people are saying you should use for data analytics frameworks like Spark. But we found a few limitations. So one of them is the performance and capacity hard drives, and the other is bandwidth bottlenecks that really arise, I think, in realistic data centers because you get organic growth over time. And so older equipment has slower networks. At the time we started looking at this, NVMe SSDs were just starting to become big and fast, and we started looking at how can we use them to speed things up. So this led to research on caching solutions for object storage and data analytics. And you'll hear about this afterwards later today. The data center data delivery network, D3N, adds a read cache to S3 gateway. It puts gateway instances on the client side of network bottlenecks. After publication, we upstream this work. If you're running a recent SEP version, you can enable D3N and try it. Careens ties D3N to the schedulers and frameworks in Spark. Like Spark, looking at the job queue of pre-batch objects before they're needed. T4N adds write-back caching and other improvements based on a flexible directory, replacing the consistent hashing of D3N. Another infrastructure project that derived our SEP experience is the Open Storage Network. This is developed and designed for sort of mini messy deployed at university sites for storing scientific data. They have a growing network of currently 8 sites across the country. We're starting to investigate using it to look at the challenges of hybrid cloud, because here one of the big problems is where data is and getting it from where it is to where you need it to be. And there's more to storage than large objects. This is another thing you'll hear about today. Volumes of virtual disks are fundamental to most of the cloud. Virtual machines run on them. Even ESI depends on them. But they've got these tight performance requirements, and it's hard to scale. So again, we learned this in the MOC. There was a large application deployment, overloaded our SEP pool, and suddenly virtual disk I/O latencies were running at about 5 seconds. That kind of ruined our day. So again, we turned to SSDs and caching. And so you'll hear about the log structured virtual disk project that uses local SSD as a write log and read cache, batching writes object storage, and preserving consistency even when SSDs fail. So it gives a huge performance and efficiency improvement over the existing solutions, and we're deep in the middle of discussions to upstream and design. So back to you, Ron.
So all that storage research, most of that's either upstream or is in the process of being upstream, actually come back and has impacted what we're doing. The MOC ended up supporting a lot of users and actually a lot of users of services run by those users. But it was very much a best effort service. You know, it's, as Peter said, we're both scarred from the 2017 experience of losing data. It doesn't matter how many times you tell people, don't back up your data, or this is not, it does not work. If you've been reliable for many years and suddenly you get that, yeah, you gotta get those all the time. So, you know, it was also very hard to use in some sense. We didn't have facilitators, people helping. What's incredibly exciting now is we have Scott and Wayne, somewhere here, that are now starting to production services. They're taking over supporting real users, and it's been this incredible collaboration where they've been specifying their experience of setting up at scale high-performance computing services that with real users with a modest operations team, what's really required, and then Red Hat and the MOC developers have worked together with them to actually deliver capabilities that are required to actually do production services. And they're up now, and that's amazing to have institutional commitment, professional operations, facilitators, and it's driving new research. Going back to the OS level, it's there's a whole bunch more work that we've done. Rapid serverless cold start, dealing with optimizing the hardware using AI or optimizing controls over it and dramatically reducing for different workloads the energy used by the environment. The Unikernel Linux project, which is actually ended up not being as specialized as some of these highly specialized, but is now incorporated a patch into Linux that allows all of Linux to be used. You know, it runs on any hardware that Linux supports, can enable still significant performance advantages. All the hardware, all the devices, and all the applications run on Linux. To be honest, I never thought that project would be successful. It took years of iteration with a team of engineers from Red Hat and a team of researchers to actually have the capabilities so that we could turn Linux itself essentially into a Unikernel. That led to other projects, and I'm being told I have a second, so I'm going to move quickly. There's UKL is now being used by a project at a higher level. There's been a lot of big body work around privacy and security, multi-party computation. Secrecy is a research effort to do MPC as a service, and it actually exploits the capabilities of UKL to improve its performance, and can now go beyond that. They can do things like optimizing queries, so having the query optimizer go and configure the operating system in a specialized way. I'm going to have to go a little long, sorry. But projects that Morph has, fundamental security issues, hypervisors, so Morph is another project that's come out of the broader community here that does fuzz testing with hypervisors. It's literally found, I think, over 100 bugs in AVM, Q, and U, and it's all now upstream. Impact on education now through interactive open source textbooks you'll be hearing about. And actually to do that, we ended up changing some of the infrastructure, how things are deployed, and programs to actually train SREs, not for our cloud, but in conjunction with Red Hat, actually enable in a community environment like this, students to be engaged in all these projects. And then Dataverse has been a long-standing member, but our newest sort of partnership, I think, is really in the Coliseum project, which is a wireless test. So the expansion is kind of amazing. This chart shows a lot of proposals that are going to be discussed tomorrow. So to open this up to a broader community, we're embarking on bringing a UCRC and NSF industry university collaboration. And so tomorrow will be all the proposals that are going to be outlined there, as well as various tutorials. So the next part of this, John Goodhue. John's next. Excellent. Would you come up? So John's going to be talking about the executive director of the MGPC will be talking about that. Mike Zink, who's leads the Open Cloud Testnet, will be presenting on that. Then we're going to have Scott and Wayne, wherever he is, talking about the production services that are being deployed. And finally, we're going to actually have our newest member of the family, Policy and Project.
Good morning. I'll spend just a couple of minutes talking about the MJHPCC. Ron has referred to it a few times as kind of a precursor to some of this. The MJHPCC consortium, which after 10 years I still can't totally pronounce, is a partnership, really, I think of it as a joint venture between 5 research universities in Massachusetts, MIT, Northeastern, Wall Street University, the University of Massachusetts, and Harvard University. From the beginning, I think it's fair to say that we've been 3 works in progress. One is a physical entity, a data center dedicated to research and education. But overlaid on that, and perhaps more important, is this notion of kind of a virtual commons for computationally intensive research. Much of it, as you'll see, has to do with research that is outside computer systems, but the work that's being done here is an important component of that as well. And the third part of it, in part as a side effect of our involvement with the state of Massachusetts, is the notion of local impact, things that we might do in the city of Holyoke, Massachusetts, western Massachusetts, where we are located. The motivation is simple, and this goes back to the early 2000s. There has been explosive growth in demand for research computing in the university community and around it. I think there was one other motivation for the MGPCC that came a little bit later, which is this notion that 5 universities working together can often take on challenges that are larger than one single institution. The landscape that we saw then and has evolved over the past decade is one where it's familiar to all of you. Scientists doing simulation, analyzing massive quantities of data, remember a colleague at Boston University saying, sorry, we can't move our equipment to the MJBCC just yet. We're busy discovering Higgs boson. When we're done with that, maybe we'll come out. So the amount of, or the impact that this community has using the resources of the data center is forever astonishing. Just looking at our 3 works in progress, kind of at the foundation of it all, maybe level -1 or -2 in the stack, is a data center in Western Massachusetts. It's got room for about 1,000 cabinets, access to 12 megawatts of power, expandable to 24, with land for expansion if we need to, and 100% carbon-free energy. So it's a nice package. To put those numbers into perspective, something odd happened with the microphone. I apologize for that. But to put that into perspective, some of you maybe saw the announcement of an exascale computer, the first ever, at Oak Ridge, Tennessee. The building that that computer is in is about the same size and has about the same size power feed as the one that we have. So there's room for kind of a lot of computing. I'll note that that computer cost $1 billion. So I'm not sure we'll actually ever have enough money to fill that much capacity. But we've got the space and the infrastructure, and that was part of the deal 10 years ago. We opened in 2013. There's somewhere north of 20,000 research faculty, students, classes using the center, hundreds of thousands of CPUs, somewhere north of 150 petabytes of storage. Whenever I say a number like that, Scott Yokel at Harvard says, no, we have that much storage at Harvard alone, and a couple of terabits of bandwidth available into and out of the facility. About a terabit of it lit, the rest of it the technology develops. So again, being able to have a large amount of capacity so that when someone comes to us with the next big thing, we just take it in stride. Again, perhaps more important, and this is a bit of an eye chart, and I'm not going to do all of the bits and pieces on it, are the things that have grown up in the virtual commons. If you look at our stack, I've already described the data center that's down below the bottom of this stack. Networking has been an area of collaboration across the Northeast since the 80s, since before the internet was invented. And we're benefiting from that. You'll see regional initiatives like the Crossroads and Internet 2, as well as local resources from MIT and UMass. Further up, we've heard a bit about the Northeast Storage Exchange. We'll probably hear more later in the day, providing both disk and tape storage at large quantities with very good economies of scale. Above that, there's a plethora of compute resources that have kind of tested our ability to share across institutions. And you'll see contributions from, I think, every one of our members, including one from MIT, the Lincoln Laboratory Supercloud, AI Jumpstart at Eastern University, of course the MOC Alliance Systems, Community Cluster at UMass. A really interesting kind of breadth of resources that allow us to figure out how to work together to gain economies of scale. Also some regional and national initiatives, the Open Testbed, which you've heard about, Fabric, which is a NSS-sponsored networking initiative, and the National Research Platform, another distributed computing exercise that's taking a different look at how you can share resources on a national scale. And at the top, perhaps most importantly, is how we've been able to bring people together, both sharing and developing talent at the system administration level, research facilitation, and also research software engineering across the consortium, and contributing to both local initiatives as well as national initiatives. Is this better? Oh my goodness. Unlike Iran, no one can ever hear me talk. And that will allow me to, I think, do my last 2 sentences. You'll hear, we're actually very excited about a partnership with Red Hat. You'll hear from Sarah about a little bit later on. where we're working with Red Hat to take interns out of our internship program locally in Polio and moving them into Red Hat internship programs. Another touch point in a pretty big landscape of collaboration. And then just a note about local impact. Just mentioned our internships. We're crossing over 20 interns over the last N number of years, Polio Codes, where we take aim at middle school students, which is the place where we really, where kids either engage or they don't with computer science, and also national initiatives having to do with building better computer science education pathways in K through 12. Looking ahead, at each level of the stack, we're doing a little bit of work. We continuously work on data center capacity and cost efficiency, building the tracks in front of the train as it kind of comes barreling down at us. Lower friction for shared storage and compute. This conference is a lot about how we make that happen across our members. Increased collaboration on user support and software infrastructure. How do we share people that are talent that are across our institutions and perhaps also nationally? And also, before you get there, how do we expand the size and diversity of the pipeline for people coming into this community? That's about it.
Thank you, John. Oh, good morning. I've got to be careful with this one a little bit. Hello, good morning. My name is Mike Zink. I'm from the University of Massachusetts Amherst. For most of you, there is actually part of Massachusetts west of the I-95 corridor. I work like 20 miles, 50 miles north of the MGH PCC, so for comparison to you guys, it's easy for me to get there. If you ever have a chance, come out, visit us. It's a nice, visit the MGH PCC. It's a nice, very nice facility with a lot of things to learn. I'm here to talk a little bit about the, let me turn this off because I think there's some interference or whatever going on. Let me talk a little bit about the Open Cloud Testbed. Peter did a fantastic job of introducing it, so I can actually kind of skip this slide. The only thing I want to say is I'm not doing this all alone. I have support from Peter and Oran, Miriam Lisa from Northeastern, and Martin Herbert from BU, and my colleague David Irwin at UMass. So Peter told you quite a bit about the OCT already and what our plans are, and I just want to skip that to give a little bit more time to talk a little bit about the inner workings of this. So here what you see is actually what we built, and I'm not going to want to overwhelm you with you. I only have 10 minutes. There's no way I can get through all of this. There will be a poster. I have a note on this afternoon. Hakan is somewhere here. He will actually, Hakan's back there. He will talk about this. Give you much more detail. What I want to tell you is actually two messages I want you to take away from this slide. First of all, this is what we proposed to NSF, what we're going to build. All the rest you see came into place over time. Great support from industry. Two Sigma made a huge hardware donation where we used part of it. Wonderful support from with ESI and then also AMD Silings or FPGAs. But I also want to come across here is we're not only providing bare metal servers for research and making this elastically available, but we're tying in a lot of initiatives within the MGH PCC, but also nationwide. And I think that's a nice and a wonderful thing for systems researchers, because we're not doing this in isolation, we're doing this really as a nationwide effort, actually kind of going internationally, hopefully soon, once we kick out some of the legal issues on that side. So this is our infrastructure. Again, I don't have too much time. If you want to look at this in more detail, come back and post it later on. A little bit of an idea is I'm probably the first one to show really a graph here. What you see here is time on the x-axis, and then you have two y-axes where you see on the red line the resources, that specific resource we're making available in OCT, and then the blue line is showing the percentage of the usage. And yes, I give an example that's a little bit different from what Peter you mentioned, and that is here you see that at some time in the summertime over 2021, academics sometimes also take a break, so the load is really low. So you can actually, at this time, you could have used ESI to give resources, maybe to an HPC cluster, maybe to NERC, to give make those resources available to others. So it shows you that when you look at the data over time, that usage is never constant. And then you can bring in bare metal servers or give them away time. We have other examples where you see ahead of deadlines. This is going, the users going really great. And we're working here with Red Hat and other teams to integrate ESI to make this really happening so we can allocate these resources, make them dynamically available. We're exposing some of our hardware right now to the NSF Cloud Lab testbed. And so what we've done is actually that modifications the team did went actually into the code base for Cloud Lab and went into the code base for ESI. So others who would like to reproduce that came to this. Let me talk about the other exciting part we have is we're bringing accelerators into the testbed. Commercial clouds have FPGAs now, but they don't have them available as we would like to have them available for systems research, right? There's a lot of abstraction, there's a lot of APIs that keep you away from the core details. What we have done is we have integrated 16 FPGAs in bare metal servers that are available for the systems research community. They are networked, so they both have getting into details, 200 gig interfaces. So you can really do some exciting stuff on that side in terms of networking research, disaggregation research, lots of different avenues here. And the team at Northeastern has done a fantastic job in also building a workflow around this. So you can now bring up a VM with all the tools you need to create your bit stream and then deploy that on the FPGA. It's very nicely self-contained. That makes life easier, and I think that helped with attracting a bunch of people to it. We now support 15 research groups nationwide with that. This is where we come on one side where we come into international. We have some requests from outside the country to work out how we're going to do that. We got additional funding from NSF to work on smart NICs and enable P4. Some of the networking folks might be familiar with that. And working with the Fabric team, with people from the University of Nebraska and ESNet, to make this not only available on your cloud testbed, but throughout the infrastructure throughout the country. And we see right now that there's a lot of demand for these FPGAs. People not getting resources when they want them, and so the only option we have right now is actually do a build out in our 4th years of the project to get more resources available. So Ranga is going to give a deep dive tomorrow at 1:15, and that's where you can learn a lot more about the work that's happening with respect to FPGAs. I want to give a shout out to the Fabric program because I want to show you that we're not only locally connected within the MGH-BCC or within the state of the region, we're also working with a nationwide project. Actually, Fabric is an international project because we also have nodes in Holland and in Europe and in Asia. And so that is actually, I don't know, there's some people around who are still familiar with Genie. So Fabric is a little bit of a follow-on of Genie, building this international cutting-edge research infrastructure that allows you experimentation on a large scale with programmable networking, programmable storage, and actually compute available. And what we've been working on, and Paul can tell you more about this, we're actually building a connection, which they call a facility port into OCT. So now you can actually run experiments that span, the world if you want to, using bare metal servers on our side, but also using other resources across the globe. And again, we're working with the Fabric folks, and then they will put the same FPGAs we have in their testbed, so you can actually do advanced networking experiments based on P4 if you like. And Paul, who's actually coming all the way up from North Carolina, will actually give a deep dive tomorrow at 3:15 on Fabric and give you much more details. A couple of things we have in progress right now. Exposing our hardware right now through Cloud Lab, which is another NSF testbed. Many researchers in the country are used with, but there's also another one that's called Chameleon Cloud. And we thought it would be nice if we make some of our hardware also available through Chameleon Cloud because it reaches then another set of researchers who are familiar with that interface, with that API, with that infrastructure. We have the cluster up right now, but it's not ready to make it public for use, but that will happen fairly short. We're working on some of the ESI cloud integration on the networking side, on the bare metal server side. We're working to do a little bit more work on the networking side. And we're in the progress of further onboarding FPGA users. If you're interested in this, to me, talk to Sarenga, come to the deep dive later on. Outreach is one of our main missions here, so we're also gearing up for different summer programs our institutions have, working with high school students in getting them introduced to cloud computing, to distributed systems research. If you have any needs on that side, let me know, talk to me, I'd be happy to help. And then coming up in the fall, we have the IEEE International Conference on Cloud Engineering happening here in the end of September. The deadline is approaching fast, but if you have some research work in cloud or in cloud systems, please submit your paper there. There's a couple of pamphlets out there on the registration desk. If your cameras can grab the QR code, you will get to the website for the conference. Last words about the future. So when we wrote the proposal, NSF, part of the solicitation was we have a 3-year site visit that just happened in the fall, thanks to the wonderful work of the whole team. We passed that, so you got to stick around with us for the last 2 more years. It's the good news. And so we'll continue to evolve with LCT. Certainly one of the things is the FPGA build-out I mentioned a moment ago. And then there comes the bad news. The hardest part is how do we make this sustain after the funding ends? And we'll talk to our advisory board about this afternoon. We're also looking forward to getting any feedback, any insights from you guys who maybe run infrastructure in the past, research how we do this. My time is almost over, so I would like to leave you with one question, and then hopefully when you catch me in the hallway or whatever, I'd like to hear some answers from you about, especially from the research and from the open source community, what are the needs you have from bare metal aspects? What do you need? Is there new software, new hardware you would like to see so we can help you advance your research? With that, I want to thank our industry partners, Red Hat, AMD Xilinx, and Two Sigma have been wonderful supporters. Also, what's really important for me, I want to thank the students, the undergrads and the grad students that have been working on this project, and our research engineers and scientists, because without their hard work, we could not be where we are. Thank you very much.
Thank you, Mike. So Scott and I wanted to take a few moments to discuss the New England Research Cloud. My name is Wayne Gilmore. I'm the Executive Director for Research Computing here at Boston University. And Scott Yokel is the Head of Research Computing at Harvard University. So when Scott and I first started discussing this back in 2018, I think it was 2018, we both had a need to be able to deal with the emerging workloads in the research community that typically don't fit in the high-performance computing space. So we were discussing whether we could build upon the successes of the Mass Open Cloud Alliance and the relationships with the Red Hat Collaboratory to build a production cloud environment to service not only our researchers within the 2 universities, but also researchers at institutions regionally in incubation hubs for small businesses in the Massachusetts region. So the vision of NERC was born, and really we were looking to do a few things. Build cost-effective production cloud resources, standardize the deployment so that it could be reproduced by other centers, facilitation with clients for effective use of the cloud. So we both have very strong facilitation efforts in our research computing groups, and we build upon that to actually facilitate researchers to use the cloud effectively. And then finally, can we take all of that usage from the production cloud environment and feed that telemetry back to systems engineering researchers so that they can do innovative research with that data. So this is where NERC fits in within the ecosystem, and like John was mentioning a couple talks ago, we have the MGH-PCC. I'll try to hold the microphone a little further away. This is the ecosystem for NERC, and you can see that, as John was talking about, the MJHPCC and is on the bottom here, and we have the Northeast Storage Exchange, both very successful projects that NERC heavily leverages. And then one of the unique aspects of what we're doing with NERC is that we're able to take innovations that come out of the MOC Alliance and really leverage the development team, so much which Scott will talk about in a little bit, and actually develop new technologies and be able to provide that within the production environment for researchers to be able to leverage. And then finally, we make the communities, the research communities and the education workforce community actually leverage the production cloud in an easy to use way. So can we have an easy access portal? Can they actually use their institutional credentials to actually access the service? And can we pair that with cloud facilitators to be able to help them get their workload running on the cloud? And currently, for NERC, we have the following 3 core services. So the first one, which is virtual machines, and that is in production right now. We have 50 investigators, over 65 projects from 7 institutions that are currently using this service. And because of this, the Mass Open Cloud Alliance has been able to shift all of their workloads onto the production cloud, freeing up a lot of their efforts to be able to work on development activities to enrich the production cloud and help it move forward. And then the second service is container orchestration in Mass Open Cloud with assistance from Red Hat through the Collaboratory. Have been able to develop OpenShift service, and we just had that handed over into production. And we'll be opening that up for onboarding on April 1st. If there's any test users in this audience that would like to try this sooner, please do reach out to either Scott or myself, and we can help you get onboarded now. And then finally, we're looking to pin up software as a service on top of that. So one of the first projects that we're working on is the Red Hat OpenShift data service, which is currently in development, and that'll provide a platform for AI researchers to be able to do their analysis. And now Scott's going to talk about some of the supporting services.
Thanks, Wayne. So one of the challenging parts, every time we stand up a technical service, is there's all this other apparatus, what we call business ops, that has to go with it. So you have to think of every service for when a researcher in some domain like chemistry or physics comes in, we're normally not completely using in the research space all of the different standard services that are part of enterprise IT in a lot of our institutions. So that means identity management, resource management, how do we give allocations of resources to faculty, how do they decide how much to have for each user, manage users, how do we support users with ticketing, with documentation, how do users know how the equipment is operating, how the servers are operating, right, with dashboards and things like that. So as in the MJHPCC, as we transition away from doing purely institutional services just for our researchers and think of this collaborative space and shared services, we don't want to have to build that infrastructure that I just described every single time. Because building out that infrastructure, for the most part, takes more time than actually building out OpenStack or OpenShift. So I'm going to walk through a few of what we've deployed, and how we've deployed these is not meant just for NERC. These are available as across the MJHPCC consortium. So one of the first parts was identity management. So thankfully, within MJHPCC, we feel like we have a resident expert. I don't know if Jim would say that, but we feel that way when we engage with Jim about identity management. And thus far, we've installed a web front end that on the back end. So the user experiences, they come to the registration application, they register their local credentials, right, with this on the back end. Keycloak is storing and matching these to a local user. That local user then can be used across any service, right? So that's nice. So on the front end, it's in common, which all institutions, most of the institutions in higher ed are a part of. So that makes that nice and easy. So anybody can come and authenticate and log in across the consortium. They can, when they do that, then a PI can go to ColdFront. So ColdFront's an application that's an NSF-funded project from University of Buffalo that we partnered with. It's a simple portal that allows you to say, I'm a user, we can upgrade you to a manager, and they can manage a project. In a project, they can add allocations of resources. So any resource can be defined, and they can also define users. Users are looked up from Keycloak because they've registered already. Once they do that, cold front, it's just a Django app. On the back end, you can push data to any system. So the OpenStack, OpenShift, all those systems get a feed of what is a project, who has access to the project, what are the quotas. All of that can be managed simply from the research room. We don't have to have tickets, do all this back and forth. They can see what their consumption is. So a couple of the other aspects are having documentation. So we're just using something pretty straightforward. We're just using GitHub.io. So we generate docs that anybody can push to. They can be on our website. It's easy for everybody to have access to them. And so we can contribute multiple ways to that documentation. So when you go to use commercial cloud, you don't necessarily have kind of tailored like cookbooks or workbooks of the types of things that you want to do. In the research computing communities within our institutions, there's a lot of like kind of rinse and repeat infrastructure for what people are building. There's a lot of what we call science gateways, right? A science gateway with a web front end, some compute engine on the back end. There's always some database that keeps information and provides a visual representation of your research, right? It makes it easy to do a wide breadth of kinds of research, especially far outside of the space of this, traditional STEM, which use high performance computing. So we can provide rinse and repeat of these kinds of environments and QuickBooks for them. The other aspect is a ticketing system. So luckily we convinced John Goodhue, hey, maybe we should all collaborate and use the same ticketing system. So we went after OS Ticket and do a hosted service. We're not having to manage our own ticketing system. But the nice part is, because we're doing it collaboratively, all the different projects can, if we need to see, and interact with each other across multiple projects, we can do that within the same system. And we also use InStatus as a way to demonstrate to the user community what is the uptime of the various different services. Every time we put in a scheduled maintenance, it automatically emails. So it makes everything systematic across all the different services so the users have the same experience. The other aspect is reporting. And so in high performance computing, a lot of the NSF funded like Exceed sites, like the tier 1 and tier 2 sites, I've leveraged this application. A number of years ago, they extended it for OpenStack. However, as we found, not as mature for a modern OpenStack deployment. So we've done a lot of work with them and have made some updates. And we also figured out a clever way to also use data from OpenShift to put into XEMod. But XEMod is nice in the sense that it's built for university style. It has a hierarchy of institutions, science, discipline, a project, a PI, users. So you can roll up this hierarchy and create nice reports from it. It has a portal that end users can log into, faculty can log into it to see how their utilization is. So that's what we're using for reporting and keeping track of the accounting mechanisms that would be across multiple different services into one single portal. So one of the other services, we talked about a few times, is the Northeast Storage Exchange. This is managed at Harvard University by storage engineer Juan Pacific. And there's two basic services at the top. There's NESI Set, disk, NESI Tape, provides tape. And so we really thought about who are the customers of NESI. And the customers in NESI are not end users. The customers are these other projects, right? So what we call the data manager or the storage manager at the other institutions, right? And so we provide some basic services that the whole point was to abstract identity management away from handing out storage. So we do this a lot of times through using Globus. So we provide file access to data transfer nodes via either StephFS, or if we do it on the tape side, we're doing it via spectrum scale. And we can hand off a chunk of storage that media is owned by the institution. They decide, how do I want to chunk it up? And they can log into Globus, right? And all of the federated identities of the Globus users from their institution can be managed through the portal, and on the back end, it's just one system user for that institution. It's a really nice abstraction. It also gives delegated administrative access. Globus is also nice because you can create user-based authentication for all the way down to a file or a collection, and you can do it for durations of time. private, you can have it be public, you have a lot of flexibility, as opposed to if you were just doing an S3 bucket and you're handing out a reader or a write, right? You can't expire that, you have to invoke that token, give everybody a new token. So it has some interesting flexibility in that space. So that's why we went down that path. And it's kind of that kind of cloud storage space that's kind of in the middle. It's not active on the high performance computing space, it's not active on other things. It's kind of that intermediary space to store things. When you think about it on a disk, on a tape, it's kind of a long-term cheap storage. Inside the data center, though, we can hand out across the high-speed network, we can hand out RPDs. Every institution can decide what to do with it. They want to mount it up with a block device, serve it out via NFS to their cluster, attach it to a VM store, they can do whatever they want to with it. And as you heard before, Northeast, so the New England Research Cloud, so in NERC, we use it across back end of our data store. I'm going to switch and give you just a couple of highlights. So it's been really interesting to watch. It's an experiment. Neither one of us have run a cloud. We've not offered that as a service to our users. At Harvard and in Faculty of Arts and Sciences research computing, in those days, we did a lot with VMs and handed those out. So we had some idea about how people might start to use this. But it's really been interesting to watch, like, faculty from history, political science come in and build out an entire data structure, right? And realizing that, like, oh, using a standard database is not going to work for what would be 100 million articles that they want to put in this data store, right? So they had a conversation with Milson. Milson was like, hey, there's Elastic, let's think about that. They built that out, some indexing on it, and they're able to search and do all sorts of interesting looks at partisan bias across the historical number of years, right? Those are the kinds of research questions that would be really challenging to ask if you didn't have resources and people to help you think about the way to do that, right? Most graduate students in history are not thinking about the infrastructure that's needed to put 100 million articles together. Right? That's one of the things that's interesting. Earth and Planetary Science, Professor John Shaw, using, needs lots of different Windows instances in order to do the simulation, in order to have graphical understanding of predictability of earthquakes. We see all sorts of, like the next one here by Professor Xiang Lin in public health. It's a really typical type of thing that we see in public health where they want to develop a portal that their research community would come and use. And on the back end, they're developing various different algorithms to be used, launched as part of the computational side of it, but it's also tied to a large database, and on the front end, it's like a community portal, right? So this is one for whole genome sequencing studies that they use within there. So Wayne's going to give a few more highlights before we finish up.
Great, thanks, Scott. So on the BU side, I just wanted to reference 3 projects, and there'll be more projects I'll be referenced in this afternoon's keynote, 4 o'clock. The first one here is from School of Public Health in Kevin Lane, and he's really interested in providing analysis on accessibility of different services, parks, grocery stores, etc. And they first set this workload up on AWS. They were looking for a more cost-effective, better solution in which to control. So we actually ported that workload over to the production cloud, New England Research Lab. And it's been very successful, and they're looking at actually leveraging that service for other research projects on the medical center campus. The second one here is a good example of a web gateway that needed to be created for researcher Stefano Monti to help identify candidate providers for cancer. And so my group through Research Computing, we helped actually develop the Arch and Apple workflow, and then we were able to port that to run on the production cloud where outside users can access it and actually use the service. And then the third one here is really the support of academics, and we actually supported our first academic course, and many thanks to Nelson that helped me actually set up all of the accounts and applications for this. But this was for computer science class on user-centric systems for data science. And we actually onboarded over 50 students who had about 26 projects that they had to do as part of the coursework. And that was a very successful endeavor. The faculty member would like to use the service again for next time he teaches the class. And then finally, just some related events for production cloud. So there's Monday afternoon Micro Talks, and so that'll be at 4:05. Nielsen will be highlighting some of the work that has been run on New England Research Cloud. And then Nielsen again will be providing a tutorial session on efficient access to the NERC computational infrastructure. So essentially providing a step-by-step guide for how you can get onboarded into the production cloud environment. And then finally, we'll have multiple posters that'll be during the poster session that you can take a look at as well. So Scott and I would like to thank you for your time.
Okay, hello, good morning. Whoa, let's check here. So I'm Emmanuel Hussein here from Northeastern University. Thank you again for having me at this alliance. I represent Northeastern University and I'm here to talk about a shared digital wireless infrastructure called Coliseum. So Art sort of mentioned this at the outset. We're sort of one of the newer additions to the alliance, excited to be part of it. I have a nice shared history with a lot of people in this room and my background working on cloud distributed network systems and RF and wireless. The hope here is to just give you an introduction of what this infrastructure is about, and then maybe just leave you with some motivating examples on some of the fundamental research and the paradigm shift that's happening in the wireless domain related mostly to cellular network systems and how that's moving more into the cloud. So without further ado, so we're here to talk about Coliseum. This is an infrastructure that was developed by DARPA, which is the Defense Agency for Research. And primarily, this was built in about 2015. They spent about 2 years and a significant amount of funding to solve a fundamental question, which is, can you actually share the RF spectrum, which is sort of everywhere around us, in a autonomous AI ML enabled way? This was kind of revolutionary about 8 to 10 years ago. And once that infrastructure was developed, it was developed for a challenge called the DARPA Spectrum Collaboration Challenge. And that culminated in about 2018, and DARPA sort of figured out, or was trying to figure out, where should this asset and infrastructure go. So us and my team at Northeastern, we put our hands up, and essentially, supported by the National Science Foundation CCRI grant, that entire infrastructure was shifted to the Burlington Innovation Campus at Northeastern University. So what we have here is basically a micro data center, about 22 racks worth of equipment, and it's 128 software-defined programmable radios, so 256 channels, and each of those radios are co-located with a bare metal x86 server with a different kind of compute form factors, CPUs, GPUs, and FPGAs co-located on each radio node. And I'll get into the architecture, how the network is sort of enabled, but the key here is to sort of understand that this is, for any of the academics in the room, a completely free asset and a resource to use. Think of it more as a larger supercomputer. You can't sort of ignore or bypass or abstract away some of the wireless capabilities or the emulation capabilities that are provided by the system, and I think that's probably more of leaning into this community and the kind of research that you all are doing. So kind of call to action for you to come check out what we have. Again, a completely free and open access resource system to use. So quickly going into the architecture here, and primarily what we have is a container-based system where essentially you have the ability to instantiate Kubernetes clusters, OpenShift clusters, bare metal access, and then basically deploy your RF wireless protocols or end-to-end network protocol stacks, Wi-Fi, cellular, name your technology, even including some military radios that you see at the bottom that can be hooked up into the system. And what you get, and this is a system that we can't take credit for all the ancillary services that are built around the back, and I think it was encouraging to hear a lot of the cutting edge research that's happening in there. This was all handed down, so this is all legacy that was developed by Johns Hopkins APL. That was the team that built this infrastructure. So we've inherited it We've augmented it, we've enhanced it thanks to the support from the Commonwealth. We got a grant from the state of Massachusetts. We obviously supported with NSF, and then have a nice cohort, a healthy mix of industry affiliate partners who've been supporting enhancing this asset or the shared national asset. In terms of some bragging numbers, so the channel emulation system, which is basically the RF emulator, which is 256 RF inputs fully matrixed in that enable you to emulate up to 65,536 connections. You're able to load on, or you're able to basically pass through about 15 terabits per second of data over a fabric of very high performance FPGAs built by National Instruments NI. And basically that's what's powering, or that's what the brain of this entire asset infrastructure. If you remove that piece, then there's nothing exciting. It's basically just an x86 server hooked up to a radio. We all have those in our labs now. So we have the resource management system, the ability to do lots of local compute, an entire kind of SDN-based or Intel-based networking backbone in terms of managing this infrastructure, differentiating the traffic profiles, the ability to load application and IP traffic flows on top of the physical layer connections that we're able to make on the Wi-Fi side. And this is an asset that was open to the NSF community early about 2020, so during the pandemic, and we're now up to about 400 odd users, daily average of about 50 odd users. We're starting to run into the problems that we heard earlier today in terms of access, conference deadlines, etc. So really looking forward to learning from this community about that. A very poor, feeble attempt at a network connectivity diagram, just to sort of grab people's attention. Happy to take a critique offline for this, but primarily where I draw your attention to is the bottom left, which are the basic, the quadrants. So these are the four quadrants, four separate racks, where all 32 radios in each quadrant are sort of hooked up with coax cables looping between the real radios. And then on top of it, basically a spine border router architecture. On the bottom right, you have our NAS storage, so about 900 terabytes right now. And then looking up ahead, we are now sort of looking at expanding and looking at connectivity and starting to think about connecting back to MGHPCC as well as other national resources like Fabric, Cloud Lab, etc., so that we can actually think about moving large-scale data as well as workloads as well as software containers between our test infrastructure and some of the other NSF funded wireless research test. Okay, so last few minutes, just wanted to sort of motivate some fundamental problems that we're looking at in the wireless RF domain at the network management orchestration level, as well as the application of AI or artificial intelligence. The picture to your right is basically a basic representation of how an AI/ML model is developed and how that paradigm is evaluated. We're looking at it primarily in large-scale Internet of Things application, where we have the ability to provide large amounts of training data, train your machine learning algorithm, develop a model, execute it on real hardware, and you have the fidelity of actually looking at what a real signal is going to do over the air. So being able to build on that large-scale emulation system a representation of a virtual world. So we're able to ingest real spectrum data, we're able to ingest real terrain models, and emulate those in the RF domain, and essentially you now have the ability to test your scenarios at scale before you move it out into a real world deployment. I talked about the paradigm shift earlier, just to really quickly give you some acronyms and where the industry and academia is moving. We have this notion of called an open radio access network, which quite shamelessly borrows from the SDN construct that this community has been working for the past decade and a half. And a poorly concocted term, but we call it the radio intelligent controller. So essentially, think of it as a controller that's sitting on your edge, on your cloud, and is essentially manipulating the RF parameters on a GNOP, or that's what we call a base station, in terms of modulating or changing the parameters from modulation coding schemes to the power levels. And all of this is being done in almost near real time in the order of sub-milliseconds. Now, as you start to sort of, pull the covers back and try to understand what the research problems there are, fundamentally, we are all RF engineers, we're not data scientists or network engineers, and that's something that we're now leaning into this kind of community, looking for cross collaboration. So we can actually implement this kind of an open programmable virtualized architecture that then our mobile network operators will someday end up field deploying. So we feel that infrastructure Coliseum is sort of one of the first ones that allows you to enable these end-to-end network architectures. And what do we do with this? So these are all the disparate components of a radio system. Again, sparing the boring detail, but looking from left to right, you have the radio intelligent controller. Each of those lines is essentially a open interface or an open API that the industry has come to agreement on. And you have the ability to self-optimize or have intelligence built in the network as each component. The central unit is where a lot of the baseband processing happens. That's where that's where the RF signal gets digitized and processed. The distributed unit is the much more of the lower level, medium access control and physical layer, and the radio unit is essentially doing the analog to digital conversion and vice versa, so ADCs, DACs, etc. This is just to motivate that. Last slide is, again, scientific drivers where we could leverage or where we could leverage your help, but also incentivize you to look at some of the research problems from our vantage point. I know it's a little bit hard to read, but we're looking at data storage problems because now we're building data sets that are sort of exceeding into the terabytes, so about 40 to 90 terabytes of data. As we capture large swaths of spectrum data, digitize it, collect the IQ samples, and now our community wants to train RF fingerprinting or channel state estimation algorithms so they can actually do this real-time or near real-time network intelligence orchestration and management. So we need help in trying to understand how the data storage community is moving along. We also want to understand how containers are being developed. How do we optimize placement of containers? How do we sort of take some of the external factors that are going to influence deployment of edge services, deployment of services at the core, and then how do we move the intelligence? Either we do processing close to the edge, or we move it into the cloud. How do latency issues come in? How does performance matter in here? So a lot of nice open questions to do it. A lot of this literature is available at coliseum.net, so there are lots of tutorials. So I'm just going to pause here and happy to have a conversation on our side. Again, thank Warren and Peter for the invitation here, and thanks for your attention.
Thank you so much. So I'm just going to race through this because we're running late. Tara, we said I had to remember something. What was it? I forgot.
Poster check-in.
Oh, okay. Anybody in the next poster session, please check in with Tara right after this, okay? So thank you for all the collaborators and to our core partners. This is sort of amazing what this is growing to. And it's so nice to be back in person. Like there's actually all these connections that are happening because we're having this big event again. Like Coliseum is a huge addition. I'd like to give a big shout out. We've got about recently 18,000 or 1,800 new servers from Wayfair that's actually being augmenting all these different infrastructures. Again, I'm going to go through this super fast because I think an important part of a workshop like this is the networking time, so I don't want to get too much into it. We're getting an economical, scalable cloud that's production. Thank you, Scott and Wayne, for research users. We have this ability to accelerate that research and the development. We've got broad industry involvement now into this initiative, that's accelerating open source. And we hope to actually take everything that's doing here, everything we've been designing with Scott and Wayne is actually in open source repos, can be replicated by other institutions, and we'd like this to be replicated and federated around the world. Much broader vision than what we had when we started this project, 2013-14. So this is sort of the agenda for today. You know, it was awesome. We saw Gloria talking about the institutional support for this. Peter and I tried to show the interconnectedness of the effort. John talked about the data center, but more than the data center, you know, a whole bunch of these projects are shared projects. They're kind of tied together in a lot of larger alliance. Mike talked about this crucial aspect of the open cloud testbed, and then Scott and Wayne the production services that are now real. And Manu this is a new opportunity. We keep hearing edge to cloud is where we should be investing. And what other place in the world could you have looked around and say, oh, yeah, we have that right here, our next door neighbors. We have 3 great keynotes today. So right after the break, Sharon Wall from the Mass Technical Collaborative is going to be giving a keynote titled The Commonwealth as a Cluster for Cluster Development. Really, this project was possible because of the big risk and investment that the Commonwealth has made, not just in the MOC to start with, but then production services and that investment, and to expand this beyond the institutions here, but to the state is really exciting. 2:45, we're going to have Blake Shiver, who's the VP of Global Cloud Partners at Red Hat, talking about the hybrid cloud. And you know, all clouds depend on open source. Really, open source is the basis for all this stuff. Red Hat's by far the most successful company with a business model around open source. And having the person leading partnerships at Red Hat engaged is both a validation of how important this project is to Red Hat, so that's great, but also an opportunity for us, because everybody partners with Red Hat around open source, and identifying and engaging the right set of industry partners as we're expanding this to enable the innovation that we expect to have happen here is really exciting. At 3:20, John Stump, the group head of infrastructure engineering, is going to talk about the broad collaboration they've been doing. John leads a massive infrastructure at 2 Sigma. Like it's amazing how big it is. It's been leaked to me over the years. Incredible security requirements and deep engineering talent that they do a lot of things that they build themselves in order to exploit both hybrid cloud and cloud services internally. It's really neat to sort of see a company with those kinds of investments, and it's been both inspiration for a set of problems that we've worked on in the MOC that we realized through our engagement with them before that we were going to hit this. It sort of teaches us some of the scale problems, and they mentored over 100 students is what we identified in projects, and hundreds of computers have come to the MOC out of the engagement with 2 Sigma. So thank you. We're going to have a whole session on micro talks. There's a bunch of these. 6 of the talks are going to focus on the core systems that have had an impact. So that whole elastic secure infrastructure you hear about, the AI ops, which is taking information from production cloud and kind of trying to control it, the unikernel Linux, the storage stack that Peter talked about, the hypervisor fuzzing project, and some of the kernel tuning with machine learning, which has had a dramatic impact on energy efficiency. Some of the other talks are talking about really important issues of workforce development, the education mission that we've been working on, and I could kill Jonathan for this, but I've been using this to write an operating system book for my course this term, which has been consuming incredible times, but it's a really exciting experience. And the idea of actually open source textbooks on top of the infrastructure we're deploying here is very neat. The CRISP project that I mentioned, and then actually the hardware software co-design. Microtalks 2, I'm not actually, this is part of the cool thing now, so I'm not that familiar with what the topics that are going to be covered here are, because we now have people that are professional that are actually working with users of the cloud. So there's a session that's jointly done by Milson from the central facilitator on the NERD team and the head of the SAIL group at BU. And the SAIL group is a professional software development that helps real applications. There's going to be incredible spectrum here where we have the heads of 4 different centers that cover everything from functional infrared stuff. I should know this. This is tested on my children back when. But anyhow, so David Bose, head of one of the centers. ASL, Doug's going to be talking about basically synthetic biology, so this is like using CAD for biology, and something I'm very passionate about. I hear that Hank is going to be talking about what they're using this for dyslexia and reading. So you're gonna have 4 heads of centers, and then I think Will's gonna give an overview of the kinds of efforts of different applications that are coming onto the cloud or that are on there, and those will be talking about projects across all the different universities. There's 2 sessions on posters today, and actually, sorry, 2 sessions tomorrow. I believe they're all filled. Really incredible. There's a set of birds of a feather sessions. You can actually follow the link or go to the table. 2 of them that I really want to emphasize that are happening today is the ESI project that I talked about, that it's the more, getting more community around that. I mean, this is a fundamental new capability. It's the center of what we've been building here. And we can shift infrastructure between all these different efforts. So I hope people go there. And then I think one of the really, really important things that's happening is, where does your data go? Are we really going to, put it into places where after we upload it, downloading it is going to cost us a ton? Where can data go from all these different universities? There's been huge efforts around multi-party computation, around differential privacy, on how to access data securely. We have now a cloud that's being operated by the research IT of some of the top universities in the world. This is a place where I think, A, we can put data, but then how do we compute on that data? So I'm very excited about a Birds of a Feather session, which this must have been Larry that came up with this title. Can MOC be the new version of the Library of Alexandria? Which, but then I guess how to make it fireproof is an addition to that. So I think this is really a kind of critical next step. Now that we have these production services, how we store the data, not just the storage of it, but the environments that we provide to access that data. And then there's other opportunities for, some of these have been scheduled, the workforce development one that's happening tomorrow, but please join in. I think that's one of the big opportunities we have by all being here in person. The second day workshop, we'll be kicking off more of it, but it's different from what we've done before. What we've done before is describe the research that's being done, right? That's what we've done in the second day, usually the MOC workshop. Here, this is about research proposals from this broader community now from across multiple universities that are engaged in proposals around this new NSF IUCRC. The way I like to think of that is the Red Hat Collaboratory really kind of engaged in a massive amount of research enabled by the MOC at BU with some bits at other universities. Now we want to involve all of academia, and we want to involve a much broader set of companies in it. And we're going behind the NSF IUCRC program for that. So you'll have the Vice Provost for Research at Northeastern and John Byers, Associate Dean here in CAS, talking and introducing this. Peter and I will give an overview. And then we have keynotes from Hugh Brock, and Larry Rudolph, who have been sort of really the sponsors of the research that's been going on till now in the MOC from Red Hat, talking about why they're investing in their vision of this larger center. Then we're going to have Mohan from NSF describing kind of the requirements of the IUCRC. And then in parallel, we're going to have tutorials that are open to everybody, everything's open to everybody, but that will be going deep into FPGAs, into how to use the NERD production systems, along with a set of talks from broad faculty, and then the same for the afternoon session, where open differential privacy is kind of one of those tools that's been under development for a while to enable access to these data sets, and Fabric, which you heard about in Mike's talk, which is, and Mike has an incredibly dated picture, by the way. It's 2 terabits, not 1 terabit across the country, and it goes to many more countries now than what he did, so that's embarrassing. But anyhow, it's talking about Fabric, and we're going to be able to connect, terabit links across the country into NERC, into OCT, all these mechanisms. So again, we have access to an incredible spectrum of nowhere else can do this, but how we tie together all of this stuff for different projects. Given timing, we'll be covering this at the start of the session tomorrow. These projects tie into everything else that we've talked about. These are the 2 tutorials. These are the second set of research talks. But again, we'll cover them tomorrow, and I hope I will not have lost anybody by this. And just, there's a couple very short closed sessions, one for industry feedback on the proposals, which is industry and faculty, and that will be a small part of the agenda, I guess, tomorrow afternoon, and then posters will be in the small hall. Anything else I should be saying, Tara and Nancy? And then the reception will be tomorrow at the brand new building over here at 6:30. All right. I'd like people to take a break and make sure we don't dig too much into it. So sorry for the breakneck speed of it. Thanks, everybody.
Okay, up next is our first keynote presentation. Sharon Wall is the Portfolio Director of Research and Development Fund at the Innovation Institute at the Massachusetts Technology Collaborative. We call it MassTech. MassTech is a state economic development agency that strives to strengthen the competitiveness of tech and innovation economy by driving strategic investments, partnerships, and insights that harness the talent of Massachusetts. Working at the intersection of state, industry, academia, nonprofit, and other key stakeholder communities, the Innovation Institute supports the growth of priority industry clusters within the Commonwealth's technology and innovation sectors. The MassTech Collaborative provided the original funding for the Massachusetts Open Cloud Alliance back in 2014 with the $3 million collaborative research matching grant, and we have had their instrumental and continued support since then. In her role as Portfolio Director of the R&D Fund and the Innovation Institute, Sharon oversees fund investments in both the Research and Development Matching Grant Program and Technology and Innovation Ecosystem Awards. She strengthens the economic development outcomes, supports sector advancing research, and leverages the capital investments for outgoing benefits, as well as aligning programs and resource commitments with the fund portfolio. Prior to joining MassTech, Sharon held leadership positions at Blue Cross Blue Shield of Massachusetts, at PricewaterhouseCoopers, and at UMass Memorial Healthcare. We welcome Sharon and thank you for being here to discuss the importance of this MOC and MassTech relationship.
Thank you, Nancy, and thank you to the MOC Alliance leadership in inviting us here today. Research and discovery is what differentiates us in the Commonwealth. Massachusetts attracts more R&D investment than any state aside from California. We are a leading technology hub. I'm going to speak a little bit about our role at the MassTech Collaborative, both at the MassTech Collaborative level and then specifically about the Innovation Institute. As Nancy mentioned in the intro, our role is to strengthen the competitiveness of the tech and innovation economy with strategic investments, partnerships, and gaining insights that harness the talent of Massachusetts. We were established in 1982 by state law, and we're comprised of 5 divisions. You can see the MBI, the Mass Cyber Center, the Mass eHealth Institute, the Innovation Institute, of which I'm part of, and the CAM organization, the Center for Advanced Manufacturing. MassTech forecasts to deploy approximately $75 million in grant funding this year. With the introduction of our new administration, the Healy-Driscoll administration, we have opportunities now to also reach the federal competitive level. So not only have we focused on state funding, this administration is very excited and ambitious and competitive, as you can imagine, in their interest to seek federal funding as well, federal funding opportunities. In that, they have introduced in their budgets that is under review in legislation, matching funds to help secure those federal initiatives and opportunities. We are in the process of evaluating several of those opportunities, leading consortiums and highlighting key assets and resources and talent that the state offers in the Commonwealth. The Mass Green High Performance Computing Center is an example of a critical resource for the research enterprise. So as we respond to these grants and they ask us questions, what makes an exciting tech hub? What makes a successful ecosystem? Having capabilities and infrastructure and the talent to support those tech hubs are what should attract us in Massachusetts to those capabilities. An example of this, led by the Center for Advanced Manufacturing, one of our sister divisions, they participated with a coalition, standing up a coalition of 85 organizations, 7 states, which submitted collaboratively under actually the Mass Tech leadership for an ME Commons grant. Again, offering matching state funds, which the Healy and Driscoll administration stands behind. We had the pleasure of meeting with Secretary Howe recently for our Mass Tech board meeting, where she continues to enhance and support the excitement around these competitive opportunities. So more specifically, my backyard, the Innovation Institute. And again, I'm one of the newer members of the organization. We focus on 4 key areas to drive economic growth: university and nonprofit research and development, much of which we're talking about today, cluster development, innovation ecosystems, and research and analysis. On the following slides, I'll highlight a few of those programs and cluster development activities. The Collaborative Research Matching Grant Program is our flagship program. This program seeks to build on and expand collaboration amongst research institutions and leading technology firms through strategic investments. This is a bond-backed fund, and it requires a 1-to-1 match, with a goal of spillover impacts into the market. We target investments with a high level of technology readiness level. This is a snapshot of the R&D portfolio, a 1-year snapshot of this past year. There are certainly previous investments and continuing investments that are not listed here that have just recently been approved. As you can see, there are 6 priority sectors that are highlighted here, even though we have applications and concepts for many more. But in terms of quantum, space and defense, cyber, blue tech, advanced manufacturing, and robotics. You can see many of the organizations that we're talking about in the coalition and the alliance, the MOC Alliance, are participants and recipients of several grants. UMass, MIT, BU, Harvard, Northeastern, WPI are all listed in these discrete categories. But one example, and actually we should say a half dozen of our prior investments, leverage the resources and capabilities of the MGH PCC, and certainly the capabilities that will be coming out of the MOC Alliance. All of these investments are going to have required computational analysis and research computing capability needs. So as you can imagine, a simple example, I had the opportunity to meet with the BU RASTIC team on the robotics autonomous program. They will be leveraging these capabilities as well, just as one example. Enough cannot be said about industry engagement and industry involvement. The role of industry is critical to success for any of these programs. Our programs emphasize the role of industry for a thriving economy and the supporting talent and workforce development that is required to sustain it. The next slide truly talks about where we modified our initial R&D program and offered a new Tech and Innovation Ecosystem Grant Program, which is fairly new, launched last year, with the intent to gain real commercialization focus. Top of the TRL level, moving closer to the manufacturing readiness level. So it should align very well with a lot of the federal programs, and it was very insightful of the organization to have planned in advance to target the primary sectors that they're looking at, as well as what we're looking at, and a manufacturing component, which there's a huge emphasis to bring more of those capabilities nearshore and onshore. This program also targets shared technology systems and platforms. That infrastructure is primarily a huge example of what you're doing today. And providing funding opportunities to underserved communities in STEM. These are a few of the initial investments that are to be announced, and these are in the area of marine tech, blockchain, both of which were nonprofits, and to a university, Western New England University, to establish a fintech incubator in Western Mass. Interestingly enough, it's such a tight world. Our PI there also scheduled time to meet with John and his team to tour the MGH PHCC to look at what the capabilities were there, because many of these institutions do not have the funds or the scale to stand up the environments that you have access to. A few of the additional programs that feed this ecosystem are the Entrepreneur Mentorship Grants, which are to enable community-based incubators and accelerators to provide startup support. MTIP is about connecting students to career opportunities at emerging tech firms. So it's really important to us that you participate both at the industry and the academic level to support those internships and really get that workforce pipeline thriving. Tech Talent Diversity Initiative programs are about supporting greater opportunity and equity in tech centers. All of these components feed that broader ecosystem. I'm going to touch a little bit on cluster development. Some of the activities we have around cluster development. Initially here we're showing our FinTech activity. This is convening and collaborating with a cross-disciplinary community of FinTech innovators to align the landscape for future growth. Similarly, we're having similar activities in the blockchain cluster. You can imagine that's an interesting space right now. That's got a lot of focused attention. And we're developing activities, including an assessment of the industry activity statewide. So some of what we do also is conduct assessments to understand what resources and capabilities are in our environment that we can leverage as a community. In the robotics space, the Innovation Institute convenes a stakeholder forum. As you can see, many of your colleagues are represented here. We have folks from BU, MIT, industry, all represented in this robust robotics cluster. And I would say more mature than some of the other clusters. This is a little bit off of the area that you may focus, but it's an exciting area that also will need a lot of computational capabilities. And that's the investments that we've supported for the Seaport Economic Council for blue tech initiatives. Pretty cool stuff. Positioning Mass as the national leader in the global blue economy. Quantum computing. When we started to target concept paper responses on quantum computing, I don't think anybody anticipated it would take off that quickly in terms of the interest. Early investments in UMass Boston quantum program, as an example, has already shown strong industry interest and collaboration and outcomes. A study is underway today. Thank you to your participation. Many of you have participated in that assessment, and we hope to have that available soon. And this is to really assess our quantum computing landscape in Massachusetts. And finally, the artificial intelligence space. Artificial intelligence, as all of you know, machine learning, artificial intelligence, will consume every ounce of capability that you make available, and it will continue to grow and expand and consume. So it's very critical to understand how to engage with stakeholders in this community and drive the strategy and competitiveness that we want to have in Massachusetts. AI is a priority sector, which is of great interest to the state's economic competitiveness. Massachusetts is considered the birthplace of AI, given our long-standing reputation as a concentrated intellectual hub with big tech presence. So this all being said about what are the things that we do and the investments that we make, we had the benefit of being one of the, and I wasn't there, so I cannot take personal credit, but on behalf of Mass Tech, we were part of the initial seed funding, as was the Commonwealth directly. And it's a powerful story of collaboration across academia, the public sector, and industry in the private sector. Starting with the initial seed fund from the Commonwealth, by the state, in the MGH PCC, following with the Mass Open Cloud, and the NERC. And as you can see at the bottom of the slide, these are just illustrative, but you can see that federal funding, state funding, industry funding, all coming together and collaborating and building and growing on your expertise and your research and the work that's been done here has helped position the state not only for a very positive, strong, data-intensive computing ecosystem, but it provides us the opportunity to be even more competitive on the national stage as well. Critical investments made by industry, in addition to what we have been able to support, is a continued need. This will not stop, as I just mentioned. The computing power needed, the technology sectors that are thriving and growing, those clusters that are developing, all need a home. And they all need these capabilities. So any of the grants that we fund, we have conversations with our constituents and we ask them, if you have these significant needs, and we're reaching out into more rural communities as well, where could you get those needs rather than standing up your own architecture and your own infrastructure? Take advantage and make sure you know about what the MOC Alliance is doing, what the NERC is doing, what MGH PCC is doing, and how that ecosystem can accommodate you in your research needs. So we want to make sure that we're driving those individuals to you and driving our investments, continued investments in this space to support you and the work that you do here. Together, though, I think it'll be important, and we ask to make that call to continue to extend out to under-resourced institutions and communities within the Commonwealth. In closing, I'll leave you with one of your own professor's thoughts that I share, but that she said already eloquently. True innovation requires big tech, and by big tech I mean industry, academia, and government to work together, to collaborate together, to combine their resources and their investments to accelerate and grow. To tackle truly big problems, the government must act as an engine for academia and industry. Thank you.
Okay.
Okay, now we're going to move on to the microtalks portion of our program, and we're going to start with Jonathan Appavoo of BU and Danny Shee from Red Hat.
So I saw someone with a little 5-minute card. You're going to need like a shot caller. I'm just, setting the stage. And of course, there's always one in every crowd, so we're presenting from our own laptop.
It has to be the first one, too.
Always. Okay. So just before we actually get going, just to make this real, what you're seeing on the screen right now are the however many students taking discussions that are working on the platform that I'm about to tell you about. And here are the 360-odd students that are enrolled this semester using the platform that we're about to talk about. So we're a little ahead, but we should get going, right? Fantastic. Which means I get to use that extra time, right? Fantastic. Okay, so it's our pleasure to be able to tell you a little bit about this project, which we call the Open Education Project. And in some sense for me, it was kind of eye-opening to see what could grow out of having this collaboratory with Red Hat here at BU. And I'm not wearing my hat as a scientist today, I'm wearing my hat as a teacher. Because in the end, the idea of keeping our education about systems, fundamentals about how the computing world works, seems radically important that it's open to me. And what we were able to do was by having people who are passionate about systems education and people who are passionate about building technologies out of open platforms together with a commitment that the things that we build remain in the open source and open access to what we're building. On a more pedantic level, the project's goal is to enable both an environment and platform so that educators can create, publish, and operationalize high-quality, open-source material, meaning we don't want anybody being able to stop us from giving it away for free. So, sorry, yes, as in free beer. And that a student only require a web browser to be able to access our materials. Now, we've been very fortunate to have brought together already a fledgling community of many folks. So the work that Danny and I are going to present is really of a much broader community that is already formed. But I would like to really say thank you to both Hugh and Heidi, who have had real faith and commitment and support for this, because this is not your typical thing of getting researchers and your industrial scientists together. So in the next couple of slides, I just want to give you a quick sense of the kind of things we're trying to achieve in our systems courses. And specifically, I'm going to use my course as an example, just so you have a sense of both the things we're trying to achieve and the challenges and the opportunities that exist. So in my class, we are trying to get people to understand some very theoretically important but foundational ideas, right? Like, what is a binary architecture? What is an OS kernel? What is a file? What is a process? What is an executable? How does all this crap run at the bottom in a binary representation? What's a tool chain? Things that we older folks take for granted that everyone surely knows. These days, with iPads and smartwatches and programming in IDEs where Java and Python are your languages, folks don't have a solid grasp of even what a file is. On the other hand, we are committed that what we teach is not just theoretically nice ideas, but the skills that they get out of the class will enable them with our future classes. So I need them to know what a terminal emulator actually is, what the core Unix commands are and how you become productive, how to use, God forbid, an ASCII editor. What is Git, not GitHub? How does assembly code actually work? And lo and behold, you can actually write it. And you can debug it. What a linker is. How do you go along a tool chain with something like GCC? And that GCC is an exemplar. And for us, one thing that we really want to drive home is understanding how to debug at the binary level is a skill that you will hold on to for the rest of your life. Turns out that you also, there's some utility in learning how to read manuals. Now, this is a broad ask. We have a lot of ground to cover, so I don't expect anyone to read all of this. But, we have to cover things from our goddesses like Admiral Grace Hopper, teaching us that, look, you don't have to write assembly code. Compilation, translation is a real thing. 2, what is an address space layout? 2, being able to actually debug in a terminal with GDB. How to use Git properly, and even how to read Intel manuals. Now, there's a lot of challenges because the class I'm teaching has an enrollment of 300 people. Okay? 300 people with a radically diverse background. So that's a challenge. You have to be able to scale this experience, or you do it lip service and you don't teach anyone anything. You just give them their A's, they go home, we make money, we're all good. Now the other problem is, everything is behind a paywall these days. So much for all our cloud and open source access and operating systems. The publishers hold the keys to the kingdom. Even though I, as a professor, want to develop solid material and give it away because I believe that an education on how things work is fundamental, lest the world become magic. So, what we've managed to do is pull together a platform out of open source where we hijack a data science platform and turn it into, lo and behold, Back to the Future, a 1970s terminal environment, web accessible. But that same environment is usable for accessing and authoring information. So in my 2 minutes past my time slot, I'm going to show just 3 quick clips of videos. So there are 3 fundamental environments that we built. One is that through a web browser, my students can access an environment where when you click on it, all you're allowed to do is open a terminal. And in that terminal, we've curated all the software necessary, I'm sure you can't read this, but to write and assemble, see an assembly code and debug it, use Valgrind, look for all kinds of things that are lurking below the surface. This same environment is what we use in class to use non-PowerPoint, non-Google slides that are open source, in which we can do our presentations and at the same time we can open exactly the same terminal. Oh, okay, well, I'm not going to try to fight with this right now, but you can watch it at the poster. You'll see us pull up a terminal environment and I'll open up a terminal environment in class with those slides showing. Finally, we also have the exact same environment for authoring high-quality textbook material that we can then publish on the web, giving folks access. And again, these textbooks contain live man pages. They contain actual terminal output and sessions. So it's real. I'm not making things up. Okay. With that being said, I'll hand it over to Danny, who's also part of the fact that it also takes real technical skills to make all of this come together. I don't know if you want that or not. Oh, sorry. Yeah.
Hello everyone, my name is Danny Shi. I am a senior software engineer at Red Hat. As we've already seen from Dr. Aparu's demonstration, OPE project provides a powerful platform for interactive and engaging educational content. So as a software engineer, my focus is on the actual development work that underpins this project. Firstly, our engineering objective is develop tooling and demonstrative systems that facilitate the ability to use and extend the open education project and test framework. Now, let's take a closer look at our timelines and milestones. In 2022, we developed features for user-friendly Jupyter book content creation. We standardized container image building process and initiate a comprehensive testing framework. In the spring of 2023, we are now focused on an OPE command line tool, a pre-allocation tool, and minimizing image size as well as improving testing coverage. For our upcoming short-term goals, firstly, we are now in the process of setting up a testing cluster with self-managed roles on NERC environment, which allows us to thoroughly test and run open education project. And secondly, we will enhance our testing framework to make sure that it's usable and run and test processes are reliable. And additionally, we will continue to develop OPE image in a Fedora build. As a thumb test, in the daily build of Fedora, Jupyter Lab and Jupyter Notebook, a modified version of Jupyter Notebooks are now available. With all of this development work, we are optimistic about the possibility of adding an OPE version in a future Fedora build, once we finish all the necessary work. I want to highlight the significant contributions made by our brilliant interns. In 2022, Abraham Yellen standardized the image building process and developed both Fedora and Ubuntu-based multi-stage image build. Xinyi Wu created OPE CI/CD GitHub action workflow, and she also created an OPE textbook template. She initiated a roles testing framework for roles. And for Yixin Zhang, she integrated RISE extension as well as developed a new slides layout extension in Jupyter Lab environment. And in 2023, Griffin Herrick is now adding permission test to GitHub Action Workflow to expand the testing coverage. Isaiah Stepton is improving container image building process and minimizing image sizes. Keely is working on shortening the wait time for roles instances spawning process. He is also working on an OPE command line tool to integrate OPE features. And Eric Monson is helping Dr. Prager to create interactive textbook content for OpenOS class. Arlo is directly engaging with CS210 course content and identifying prioritized task features based on the class feedback. We are excited to see these valuable contributions that the interns have made and will continue to make. So I want to show you a diagram created by our intern Xinyi Wu. Although you cannot see the diagram very clearly, you're welcome to check back later on this slide. So this diagram provides us an overview of the current OPE active repos and branches and the OpenShift clusters that we are running, as well as the source-to-image building pipelines. With this diagram, we can better understand the relationship of different components and how they are working together to support our OPE goals. Here are some references you could take a look to know more about open education. So this includes our OPE-based repositories, Dr. Akaru's and Dr. Krieger's interactive textbooks, and 2 Red Hat talks. We encourage you to explore these resources for further information about the Open Education project. Thank you for your attention. We welcome contributions from everyone. We hope you found this presentation interesting and informative. If you have any questions or feedbacks, please feel free to contact us. You will also find us during tomorrow's poster session. Thank you again.
This is actually what the extra time was for. It was
Never let John do the first week.
always
All right, guys. You gotta just put this.
It's always a mixed blessing to follow Dr. Appleman. He's actually one of my heroes, right? So I work at Red Hat, spent some time in sales, and I'm on the Office of the Chief Technologist now. And I spent a lot of time over the last couple of years talking about the work that he and Dr. Krieger have done with the Rhodes platform and taking it from a data science tool and turning it into an education tool. So without any further ado, my name is Damien Eversman. I am the Chief Architect for Education at Red Hat.
And good morning, happy spring. My name is Sarah Coughlin, and I'm a Senior Technical Program Manager on the Red Hat research team. Today we will be talking to you about workforce development. Before we get started, I just want to ask people by a show of hands, does this phrase mean anything to you? Do you have an idea as far as what workforce development is? Show me the hands. Okay, so a lot of people do. What I want to clarify before we jump in is the definition we're going to be using today, Damien and I, when we talk to you about this, because I would bet each of us has our own idea and definition of this, and we want to make sure we're all on the same page. So, what exactly do we mean when we're talking about workforce development? So we're defining this as initiatives that educate and train individuals to meet the needs of current and future business and industry in order to really maintain a sustainable, competitive, economic environment. So really put simply, we're talking about everyone's favorite things, education and training.
So Red Hat, we've been at this for a little while. We've tried a lot of things. This is sort of a timeline here of the things that we've done that are education or education adjacent. We've had a lot of programs from our training and certification program to more direct university-facing programs like Academy, like our workforce development program, which, by the way, follows a different definition than the one we just gave you. To our research group, which you're all familiar with, and a lot of the Red Hatters that you see here today are members of. Suffice it to say, in all of that time, we've come up with a whole ton of solutions. Some of those, right here you see, this is just the logos that I was able to find. The list actually goes on and on and on. And one of the things that we've come to realize is we've created a hot mess of academic resources. So one of the things that we're trying to do now, we've started this year, and it's going to take us probably multiple years to actually do this, is to take all of these resources that we have, and all of the other resources that have been created in conjunction with a lot of our academic partners, with a lot of our commercial partners, and come up with a much better, more cohesive way to actually bring them to students. So Jonathan was talking about that just in the last session. We want to get this into the hands of learners. And right now, learners have no idea where to go to get various bits of information, whether it's training on actual products, or concepts from our open curriculum, or even access to programs like internships and apprenticeships that we've started having.
So as Damien just mentioned and John mentioned earlier this morning, Red Hat Research, we've recently collaborated with the MGH-PCC to pilot an apprenticeship program with a real focus on experiential learning. So why really did we feel this topic was relevant at this workshop? Well, we have folks from industry, research IT, academia, and the open source community at large. And I at least like to think the idea of engaging students in creating an educational environment where they are getting real-world, hands-on experience working in open cloud software environments is critical to all of us. I would like you to prove me wrong, but again, I'm hopeful this is important to all of us. And workforce development really needs a combination of training, as Damien mentioned, something Red Hat can offer up to help with, experience, something hopefully IT groups can offer a lot of help with, and hands-on exposure to hardware, systems, and software, something that I think industry partners can also get excited about. And as Ron often likes to say, the whole really is greater than the sum of all of its parts. So we'd like you to join us at our BOF happening tomorrow from 12 to 1.
So we're open to have really an open and honest conversation about the pluses and the minuses of all of the approaches that we've taken over the years, both at Red Hat and within industry and within the academic community. We're really looking for a way to make all of the resources that are available to learners more cohesive and more available. So we'd love to see you and hear what your thoughts are. Thank you.
Yeah, hi everyone. My name is Apoorv Moon, and I'm a staff research scientist at IBM Research. And with me, we have
Suman Chen. I'm a principal software engineer at Red Hat.
So you heard Oran briefly talk about ESI, and we are going to overview what we did in the past, what's the present, and what's the future of ESI. So I mean, in the 5-minute presentation we are going to do, if you want to sleep, okay, just focus on this one slide. So what is ESI? ESI stands for Elastic Secure Infrastructure, a system architecture to enable rapid and secure multiplexing in a data center. And to achieve this, what we did at MOC, and this is like just not me, it's like a lot of my peer PhD students, a lot of engineers. Some work was also done by Oran and Peter and other professors, but that's a separate discussion. So we built a framework, we proposed a set of microservices and how they should interact with each other in order to achieve this. So yeah, now you can sleep. So, but why we need this? Why was ESI conceived in the first place? So there existed virtualization layer, which essentially provided elasticity, improved efficiency of your aggregated data center resources, but still there are a lot of use cases that wanted bare metal access. As Peter mentioned, as an OS researcher, he wants access to the hardware, right? There are organizations such as financial institutions, 2 Sigma is here, who want direct bare metal access. They don't want any virtualization layer. USRF was another use case, right? So what in a traditional data centers, what these organizations do, they set up these bare metal silos and essentially set up a lot of these silos in the data center running specific frameworks to control specific workloads. For example, people are aware of Slurm, OpenStack, OpenShift these days, right? But one thing that they miss is they do not try to move infrastructure between these silos due to various either security reasons or operational reasons. And Because of this siloing, what happens is your aggregate efficiency of your entire data center reduces. So let's see example. So what we did was, as a part of our journey, we analyzed various traces from production clusters. For example, here on the bottom, you see 4 different plots. I know it's hard to read, but one was from Microsoft Azure, where we looked into what are their aggregate usage pattern or aggregate allocation pattern for their virtualized instances. Similarly, we looked into some data from another time-sensitive workload from 2 Sigma, where we saw like there are huge gaps in what is the actual capacity versus what's the aggregate or allocation patterns. Then we looked into some batch style clusters, right? Where we have this one from the Open Science Grid project, where you see burst of workloads coming in, and these are all single node jobs. Another one is from the Mustang supercomputer cluster, where you have long queues. So what we thought was, what if we were like these clusters were actually co-located in the NGHPCC like data center. So if you do that, your aggregate capacity basically increases to this dotted black line you are seeing here. Your aggregate allocation is this magenta line, and you have a batch queue that you can potentially serve very fast with this excess capacity. However, if you want to do that, there are certain constraints that you need to keep in mind. For example, 2 Sigma might be allocated, like reserving these resources for failure. But if you aggregate them, you get more resources from other co-located clusters to manage those kind of failures. But in order to leverage extra resources from co-located clusters, you need to have elasticity at the bare metal layer. So we identified 3 key aspects of how to achieve secure bare metal multiplexing or secure bare metal elasticity in such a co-located environment. And the first important requirement was dynamic isolation. I'll briefly overview about what this layer is and what we did to achieve it. Then we have had something called for software stack setup and resetup, because we need to move infrastructure really fast across these different clusters. And then if you're operating in a multi-tenant environment where co-located parties do not trust each other, you need to ensure that when you are moving this infrastructure, and if the infrastructure was compromised by a previous entity, you should be able to figure out before you hand it out to the next entity. So briefly going over this, so for this entire ESI, Elastic Secure Infrastructure, we proposed 3 primary microservices. First was the network isolation service, that is a very minimal layer, like an exokernel-like layer that manages your networking infrastructure to ensure isolation between different clusters. The next layer we built was for bare metal provisioning, and this is a diskless provisioning approach where we disaggregated the state of the machine to a backend, and we exposed the boot images from an RBD Rados clock device and booted the physical servers out of it. And finally, we added trusted boot and remote attestation using Keyline on top of it. And this entire architecture we refer as ESI, which enables rapid and secure bare metal multiplexing. So we evaluated our system, our prototype systems that we developed, and there are a lot of results. I'm not going to go over all of them, but these are some of the highlights we can talk offline. So this was what we did in the past while I was a graduate student here. So Min will talk about what's currently happening, how they are implementing ESI in real world using OpenStack.
So as Cor said, I'm Min Chen. I'm a principal software engineer at Red Hat. And for the past couple of years, I've been working on ESI alongside a talented team of software engineers. And I'm just going to give a really quick view into our development efforts at ESI. So first, there's two quick practical definitions of ESI. First one, ESI is just a multi-tenant bare metal cloud where users can come in, use a couple of nodes, hook them up to a private network, create your own isolated bare metal cluster. It's also a place where multiple organizations can pull their hardware together into one cloud. And under such a scenario, if you put in the hardware, you're by default, you're the only one that can see your nodes. You can use it however you want, and other people won't even be able to know those nodes exist. You can choose to share those nodes if you want, but that's completely up to you. The second view of ESI is really right now just OpenStack. And you can think of it as a specific configuration of key OpenStack services, namely Ironic and Neutron. When we started working on ESI and discovered that there were a couple of features needed in OpenStack that were missing, we worked to implement them in upstream OpenStack. And what that means is that if you have an OpenStack installation, version Wallaby or more recent, then in a certain optimistic sense, you kind of already have ESI installed, right? But yeah, that's pretty great. Now, we do have a little bit of code that's written on top of the OpenStack stack, namely ESI Lead, which is a very, very simple leasing service. And all that does is it keeps track of leases and causes the OpenStack Ironic APIs to assign and unassign nodes to particular users. And you don't really need it. You can do the same thing with the OpenStack Ironic API and a spreadsheet. But ESI Lead does almost a bunch of things and makes reporting a whole lot easier. So for the past year or so, we've been focused on usability testing. And the first question there is, do the OpenStack APIs have the functionality we need? So with nodes, can we configure and manipulate nodes? Can we control the node's power states? Can we have a node boot from a volume or boot from an image or boot from bits? And so far the answer has always been yes. The OpenStack Ironic APIs are pretty comprehensive. The other thing we've looked at is ML2 networking. And here we're asking, can a user create a private network with its own VLAN, and then use OpenStack Neutron commands to configure the switch so that the node is on that VLAN? Again, the answer is yes, that works. We did have that support for a couple of switch types, but I found that really simple because I didn't have to do it. But if you talk to Naveed, who did do the work, I think he will tell you that it's actually pretty straightforward. One thing we did discover, though, is that a lot of the workflows we wanted to do took a lot of OpenStack commands. So, for example, attaching a node to a network, you need 5 or 6 OpenStack commands in order to do that. So what we did is we created a Python ESI client, which is an OpenStack CLI extension, and all it does is it calls existing OpenStack APIs and chains them together, so you can take those long workflows and use a single command. So attaching a node to a network, one command. Viewing the network configuration of all nodes, using the base OpenStack CLI, you need 5 or 6, again, CLI commands per node. So you have 20 nodes, that's 100 commands. Using a Python ESI client, you just need to run one, and you get the output in nice table. So once we were done with all that, our next question was, does ESI support practical architectures? So we started with a very simple test. We installed a keyline on the node, created a private attestation network, leased a couple of nodes on ESI, and then just attach those nodes to the private attestation network and verify that keyline could attest those nodes. And yeah, that all worked. It was good. Our next test was a little more complicated. We installed an OpenShift cluster on ESI nodes, and using the OpenShift assistant installer. Again, the answer turned out to be a lot simpler than we thought it would be. All you have to do is lease a couple of nodes on ESI, configure the networking, configure the nodes so that they pull down images from the assistant installer, and you're basically done. The assistant installer will take care of the rest, and at the end of the day, you'll have an OpenShift cluster. So that kind of speaks to how we really want people to use ESI, which is kind of as little as possible. You're going to use ESI to lease nodes, do some network configuration, configure the nodes a little bit, and then you'll use your own tools to do whatever it is that you want. You don't care. So recently, we deployed ESI in the MOC. It's a HA OpenStack installation. There's 30 nodes on 3 switches, and we're constantly adding more. Currently working with onboard researchers to gather feedback, mostly using a lot of documentation. And if you're interested in trying it out, you should just let us know, and we'd be happy to hook you up. So, key takeaways. Number one, ESI works. MOC ESI is available for testing now. You can deploy your own ESI installation just by deploying OpenStack. And we welcome any feedback and contributions that you might have. And if you'd like to talk some more, we have a Birds of a Feather session at 1:15 p.m. in room 315. We have a pretty nice website. Yes, today, yes, definitely today. We have a nice website, and you can find our team on IRC in the OFTC network, in the MOC channel. Thank you.
Do I use this or this one? Doesn't matter. Okay. Hi, I'm Ayşe Coşkun. I'm a professor here at BU, and I'm going to talk about our AI for CloudOps project. So this is a large project funded by the collaboratory, started last year, and I lead this project along with my colleagues Gianluca Stringini and Helen Liu. And we have an excellent team of PhD students, some of whom will be presenting posters in the poster session today, so please do check that out. And if you're around tomorrow, we'll talk some of the more forward-looking open problems that we would like to address in the future, so we have a talk tomorrow as well. I can't see my slides here. Right. Okay. I guess that's why people are using this microphone. Does it work? Yeah. So, cloud is a layered complex software which is deployed on heterogeneous software, and the overall hardware-software environment is diverse, heterogeneous. Software is deployed on a daily basis and updated multiple times a day often. So all this lively, diverse environment creates problems when you want to improve efficiency or diagnose problems fast. So secure and resilient cloud is a must for all businesses that are running on the cloud. But the existing practices are fragile often, so they often rely heavily on manual expertise, somebody who knows everything to come in and write a script to debug a problem. Or, we end up spending lots of time and money in figuring out problems, and sometimes we just cannot figure out problems. So at the same time, in tandem with all of this, one thing that's worth noting is that AI, or broadly machine learning, has reached a stage where it's everywhere. Like we saw in one of the other talks earlier that AI is taking over many compute cycles today, right? But when we look into how computer systems are managed, we don't see much impact of that yet, right? So there's some of machine learning used, especially in resource management, but there's this gap between where AI is today versus how computer systems are managed, which heavily relies on expert involvement today. So our goal in this project is to bridge this gap and create this rich, useful, practical set of methods, ops functionality to the cloud in a coherent, unified way as much as possible. So we want to provide this end-to-end in a way that starts at the development stage. So while people are coding, they should already gain some insight into whether they are doing something wrong. Like if you type and include a vulnerable package, we should be able to detect that and warn you before you do anything with that code further. At deployment stage, when the software is being installed, again, we can have machine learning engines essentially determine if your package actually involves some other thing that wasn't updated, or that's vulnerable, that's known to be vulnerable. And finally, at runtime, we'd like to make sure we identify rapidly performance problems, bugs, and the like, and then resolve them as soon as possible before they create bigger problems. So this is how we envision our real-time quality assurance framework to look like. So you have a Jupyter notebook, for instance, you can have a different environment as well. And then while you are coding, while you are deploying, and then when you are running things, you can see these warnings. For instance, the yellow bar over there shows a problem about an outdated module you just included in your code. The orange one is basically pointing out to a known SQL injection vulnerability that comes with a package. The pink one is showing a performance problem. You change something in your code, now your code takes much longer, and here's the profile associated with that piece of code. So we'd like this to happen in a really easy-to-use way for the developers as well as for the administrators. So I'll show you a few things briefly, like what's happening in this project, how we accomplish this vision of AI for CloudOps. And like I said, tomorrow we'll talk more about the forward-looking problems. So one way that we look into the development side of things is that while you are coding, this engine called Pirate is going to come in and mark up anything that is known to have a vulnerability. And we would like to we develop this in a general enough way that you don't have to train a separate engine for every single problem, but basically machine learning gathers a lot of data from known databases, and then in the back end accomplishes this, and while you are coding, you can already get warnings about what you are not supposed to include in the code. At deployment stage, our machine learning empowered engine Praxi, for instance, can create footprints out of the files that your software is installing, and then compare these footprints in an efficient and really fast way to known problems or known vulnerable. It could be buggy code, it could be vulnerable code, again in known databases. So in this way, when you install something, you wanted to install Keras, but it actually came with a known vulnerable version of TensorFlow, which you didn't have an idea about. So it's going to mark this for you and show you right away. And then finally, at runtime, analytics is going to provide you with the capability to diagnose problems. Problems will happen inevitably, but can we detect and diagnose them and localize them fast? So our distributed tracing method uses online learning to determine the most efficient traces that are required for a given problem as fast as possible, with using as little storage as possible. So that's one line of research that we have some nice outcomes that you can see in the poster session. And then a big part of runtime activities is to actually look at data, right? So without data, we wouldn't be able to learn anything or diagnose anything. And part of the problem is this data often has privacy concerns. Like, you want to get data from your company, from your institution. You may not be willing to expose everything about your location, about your IP, about your other sensitive information. So we have methods that take the actual data and then apply methods on it, again, actually partially based on machine learning, and then keep the fidelity of the data while providing differential privacy properties on this data. So, off to Heidi.
Hi, so my part of this project is to try to figure out how to take the data that we have in our operating environment in the MOC and in NERC and make it available to the AI Ops project, and how to support the work that they're doing and make it part of our operations environment. So there were two main challenges to that. One is to collect the right data, and the other is to provide access to the right data. So you can think of it as if there's a big field of blueberries out there, and I've gone and collected all of these, but I don't know who wants blueberries, and I don't know which blueberries they want, or if they all want pie. And so I'm trying to figure out from the people who are here today and people who are listening online, tell us what kind of data will make your research go better or make your operations go better, so that we can organize that and start iterating with Aisha's team and with the ops team to make that possible to use in the builds that we're doing in Mass Open Cloud and in NERC. So just a really quick list. You probably can think yourselves of all the kinds of data that we might have, because most of you have run clusters before. One thing to point out is that we have multiple clusters and we have multiple different infrastructures, as you probably saw if you were looking at the slides that Aran was going through earlier. And so the tools that we need to be able to handle the idea of there being multiple clusters and there being multiple ways of pulling data. Instead of just going and pulling APIs, which is a perfectly good way to gather some data, we actually have tools that are already in the operations environment that are pulling, storing, archiving, rolling over the data, and there's in particular a tool called the automated cluster management, which we're using a lot of in operations. Chris Tate, who's the man in the red hat, and Lars, who I can't see at the moment, but he was sitting at the same table, can give you all the details on how that's implemented. There's also a link at the bottom of these slides about how that's implemented if you want to hear more about what we've got. One other thing to mention is that there is such a thing as events in our operations. So it is possible to pick things out either through an AI ops model or through normal collection and correlation of data and cause that to generate alerts to people who might care. So not just the single developer, but a larger group of people who might be working on a project or a larger group of operators and admins who are supporting an infrastructure. So we're interested in seeing how we can adapt that. Going to the second problem of access, Aisha already touched on this somewhat, which is we need to provide access, but we also need to protect data privacy for the users and for data that might be part of projects and applications that are in our different infrastructures. So we want to provide as much access as possible. Right now we're focusing on the projects that are part of the MOC and the Red Hat Collaboratory, but if there are other projects out there who want to become involved in this effort, we'd love to hear from you. We're also considering the possibility of developing data sets that could become actual benchmarks and training data sets for the wider community to use. So if there's a set of data that we record that shows certain operational issues occurring and somebody wants to get access to all that to use as training for a new model, we hope to be able to support that kind of an idea. And last of all, just want to point out that because this is a live infrastructure and we're changing versions and we're upgrading and adding new software all the time, that means that the data is changing over time and people's experiments tend to run for a long period, so we have to deal with the issue of how to reproducibly collect data and how to store all of the associated information about what was running in the environment at the time, so that when you go to publish, there's enough background on what was happening with your data. So we're working on this with Aisha's group and with operations, and feel free to get us in the BOFs or talk to us in the hallways if you're interested in more info. Thanks.
All right, so good morning. What do I do right now? Oh. Oops. All right, welcome everyone. It's actually afternoon, not morning. My name is Rudolph, and I'm here on stage with Mo from Red Hat. I'm from Boston Children's, and I think we took the idea of microtalks a bit too seriously, because I think we only have 2 slides, or 3 slides. But I'm going to ad lib a little bit. We're here to talk about this project that we've been working together on for about 4 or 5 years now. And it's called CHRIS, and it used to stand for Children's Research Integration System for Children's Hospital, right? Boston Children's Hospital. But we kind of realized there's nothing really children specific about it. And there's nothing even specifically Boston Children's specific about it either. So we just called it CHRIS. Now it just is CHRIS, which means the CRIS research integration system. But I was kind of hinting that I'm at Boston Children's, which is where I am. I'm a researcher there in kind of neuroimaging. And there's a huge gap in medicine, which you may or may not be aware of. And that is, I think we like to think that medicine is pretty up there, pretty advanced with computing. The reality is it probably isn't as up to the forefront as we might think it is. There's a lot of sophisticated equipment, but there's very little value added to any of the data that is collected clinically by any kind of computation, any kind of automation. It really doesn't exist. There are lots of reasons for this, and I can talk at length about why I think this is the case. But it really is true. We have human experts that look at data, and that's almost the whole story. It really doesn't do much beyond that. And it's been a problem for a very long time. And we live in this age of AI now, this age of AI hype, I almost want to say. I can say that because my background was in AI, so I can say what we're doing now is a lot of hype around AI. And I often think that folks have gotten the idea that before AI, computers did nothing. That before AI, computers just ran Excel or a web browser or an email client. But the fact is we've been having scientific software for 50 years plus. And why hasn't this huge library of scientific software flowed into more industries, especially in medicine? So the idea of CRIS really was one bridge that we were developing to cross this huge gulf, right? How do we get research computational research that folks like myself might develop in the lab, out there in clinical service where it can make a difference? So think of it as a bridge. We have a picture a little bit later. But doesn't really tell you much, right? But what is CRIS behind the scenes? Well, it's kind of like an Uber scheduler, container scheduler is how I would describe it, with a very friendly front face. And it was geared to make researchers who don't know much about programming, right? Even though they do computing, they might not know what Docker is. They might not care to know what Docker is. How do we get folks like these to get their code out there where it can be useful? How do we connect that code to a clinical service where it can be used by people who don't even care what happens behind the scenes? So that's what we try to do. So it is a completely through and through open source kind of system. It supports at its back end a whole bunch of environments like Docker, Docker Swarm, Podman, Kubernetes, OpenShift. And the idea here is that if you are developing something, you don't need to care about Podman. You don't need to care about what is OpenShift or Kubernetes. You just write your app. And CRIS will help you. It'll give you this friendly way to, with very little extra work, have your app containerized. And now with no extra work, you can run this on any number of backend environments. So one of the things, so the kind of things we're trying to do at the moment here for the next following year is we're looking at exploring new backend environments that we can bring into this kind of CRIS ecosystem. Stuff like Minikube for like edge computing. I should take a step back and say our idea of containers in CRIS, what we've spent a lot of time doing is the idea of a workflow of containers. Right? It's not that you put all of your analysis in one big container and run that. You keep your containers as little tiny things. One that just does image conversions. One that just strips out tags from some XML file. One that might run some kind of AI compute. These live always as their big separate containers. But what CRIS will do is we'll bring them together for you in one unified experience where every container can actually run on a different environment at the same time, within the same workflow. So we're looking at cubifying CRIS to put in a Minikube. And we're also doing something which I think Ro can get information.
Hi, I'm Mo Duffy from Red Hat. These are just two projects now we're looking at starting up in CRIS. We're actually participating in this round of outreaching, and these are two of the projects that outreaching interns will be applying to. also interested in working with grad student, if any grad students here are interested, on the HIPAA Safe Cloud project. But I'll just start with the project we call Chris in a Box. We've been doing a lot of work over the past year getting Chris fully OpenShiftified. And one of the advantages that the completion of that work will give us is that we have the opportunity to then create a microchef version of Chris, which, you know, we hope at some point could help organizations maybe without a lot of computing resources use an edge computing device to do some local compute and then potentially ship additional workloads, say to Boston Children's Chris, for more computation if we want to do that kind of, you know, infrastructure sharing. The other project that we're looking at starting up right now is HIPAA Safe Cloud. So this is something that Oren mentioned earlier this morning. In the past, Chris has done work with the multi-party compute algorithm. We have an MPC plugin. This is sort of the next stage of that compute. We're trying to make it so that we can actually store data in MOC in a HIPAA-compliant way to not just enable Chris, but other projects that may have that kind of restriction on their data. So this is something that we're actively trying to sit down and figure out, okay, what are the next steps? We have the MPC plugin now, what's next? And that's the last slide. Oh, yes, and then the demo.
Okay, we'll see if this works quickly. This is just a quick teaser about an actual workflow that is live. And what I'm going to just show here, I'm going to click on this link, I think. Oh, okay. So there are a whole bunch of steps. The blue subway stops on top. Each one of those is a separate container that Chris will schedule, and it will provide this kind of, oh, okay, I guess not.
Did you have it?
It's just a link. Oh, okay. So here it's giving this like super fancy feedback to a system that's running on its own right now, collecting an image. It is now going to push it to Chris. Each of these is going to be a separate container. Now Chris is running its backend algorithms, right? This is one that's trying to find landmarks using AI. And the point here is to simplify the process of just measuring a leg. You want to find how long a leg is. Because oftentimes, there's a difference in leg length, and it takes a clinician 5, 6, 7 minutes to do this. Right now, in clinical practice, what they do is they sit with a mouse on their screen and click here, and visually click down to the next one, look what the UI tells them the length is, write it down on a piece of paper, do the next one, the next one, the next one. That's the workflow in 2023. So here we've automated this kind of super simple, really, but non-existent benefit that we're trying to add to the system. Right?
Go up.
Hi, my name is Eric Munson. I'm with Larry Ribbon. We're going to talk a little bit about the Unit Next project and how we apply a general purpose operating system from unit kernel optimization system.
Can't hear you very well.
All right, let's try this one. Is that better? I think it's I'll go with this. I will try that first. All right, great. So first, we're going to talk a little bit about what is a general purpose operating system. So we've had decades of work in engineering work and research work set up to ensure that we had process isolation so that multiple people, multiple untrusted entities even, could run applications on a single operating system. And we come up with a diagram that looks something like this. We have two users, processes that are running. They're both running on the same kernel. The kernel has a lot of infrastructure built into it to isolate these processes and to ensure that they can't interfere with each other. But it's not quite that simple. Modern deployments actually do something more like this, where you have every process, every user has their own deployment of an operating system that lives on top of the virtualization layer with another operating system or hypervisor underneath, right? So we have all of this infrastructure built into our general purpose operating system to enforce isolation that we're not actually really using, right? You don't have multiple untrusting users running on the same kernel. That's not really a thing that we do anymore. Right? So with this notion comes the idea that, well, do we really need to pay for this anymore? Do we really need to have this general purpose operating system? And so there are, the idea of a unikernel or a library operating system is sort of taking on some interest, right? And so what this is when you take the bits of the operating system that an application needs and divide it into a single binary with the user's application. And then you run that just as its own operating system. Right? And so there's a number of different projects that approach this, right? Starting with clean slate implementations, which don't harvest any code from working operating systems. They start from scratch and re-implement everything, right? Great idea to provide you with exactly what you need and only what you need, but maybe it's going to be a little bit tricky if you aren't an operating system developer yourself, and if you need something that the library doesn't already do, okay? And you can see there's examples. Barrage, FRT, Artifacts, Unicraft, a number of operating systems out there that take this approach. You also have systems that try to split this. So you'll have some reused kernel code that lift out specifically the Arch-independent kernel code into a library and provide that to the application and trying to minimize what the actual underlying operating system is doing. Namely, in this case, platform support and hardware support, and that's it. Right? So we're sort of discussing here what it means to be an operating system and where all of this code lives across a separation in privilege. And finally, you have systems that are incremental, which don't require a whole lot of new code, but they also don't provide the same level of flexibility that a full implementation would provide you. So you have a standard operating system with all of the entry and exit points that you're used to. But in this case, you take a process and you move it into a more privileged layer. So it has some more access, some faster access to the operating system, but you don't provide a whole lot of extra flexibility with this. Okay, so we talked a little bit about unikernel advantage. Let's get a little bit more explicit about that, right? So one of the things that you're provided here is that you don't have the same overhead from system calls because you're not transiting a protection boundary anymore. That protection boundary doesn't exist if you're linked together. Right? You don't actually have process isolation because we don't necessarily have the notion of a process, and we certainly don't have the notion of a process from which we need to be protected, right? And you don't have a scheduler anymore. We don't have processes. We don't need a scheduler, so we can just run whatever the application we're supposed to be running is. You get significantly improved things like boot time, and because you do jobs like hardware breakup, you offload that to the hypervisor. One of the things about requiring virtualization is now you no longer have to care about every potential network card or every potential disk controller you could be using. That's just going to be handled by the hypervisor, and we're not going to worry about Arch-independent code. And finally, you can really strip your image down so that it only contains the code that you need, right? Both in your user application and in your operating system, which can lead to significantly smaller images, which also contributes to faster boot times. But, and this is a big but, most of these unikernel systems we talked about, aside from the incremental systems, they don't provide Linux or even POSIX compatibility. They don't guarantee any of this. Often they will give you some wishy-washy terms about we support maybe 20% or 30% or 80% of the POSIX API, but even if they support that API, they don't have any of the implementation quirks that your application might be relying on from a specific POSIX implementation. Rewriting your code for an operating system with an API that you're not familiar with can be really tricky, even more so if you don't have niceties like really abstract memory management or process scheduling or any of the things that you rely on generalized operating systems to provide to you. If you don't have those, now you're responsible for writing them. If you don't have the depth of understanding, it's really tricky. It can be really hard to debug both performance and correctness in a system that doesn't support things like processes, right? How do you have GDB code running with your application if there is no notion of a process, okay? You also, for most of these systems, especially the full implementations, they require virtualization. This is not an option. You can't boot it bare metal. You have to boot it on top of a hypervisor. And that may not be what your application wants. You may not want to pay the virtualization overhead for this. And finally, all of these clean slate implementations, they are a clean slate implementation. There's not the years, the processor years, or decades even, of a system like Linux that has been running in production for decades on CPUs. And we understand how to debug it. We understand where performance bottlenecks lie in the system. But with many of these clean slates, it's all brand new. So let's talk a little bit about what the UKL project did. So our notion was, we want the ability to apply unikernel optimizations to a system, but we don't necessarily want to have to rewrite everything. In fact, we want to provide a developer with the ability to take their application that they have in user space, modify no code at all, simply rebuild and relink, and now you are running inside the kernel, right? And that's exactly what we provide. This is sort of an illustration of what that is, right? You'll notice that we have the same sort of picture that we had, including support for user space processes in the system as well. But now we have an added node over here on the left that is the UKL process, which uses the same entry and exit points that a standard user space process does to interact with the kernel. These are just now function calls as opposed to system calls. So that opens up the potential of some really interesting optimizations. These four are the main four that we explore in the paper. However, because of time today, we're only going to talk about one, which is allowing an application to directly interact with kernel services without having to go through the standard system call interface. So to give a bit of a concreteness to that, what we have here, we show the three different models and the entry-exit points that are used by the various UKL implementations. So from the previous slide, you saw that the base model up there, it talked to the entry-exit code for the standard kernel system calls. We have a model that bypasses some of that, but leaves in all of the disambiguation that is done in the virtual file system layer for the Linux kernel. But finally, if you really know your application, and you know that it's not going to need that disambiguation, you could reach directly into the networking stack, say, and call the TCP functions underneath directly. Let's see some results of actually working with this. So what we have here are the probability distributions of the latencies on calls to a Redis server. This one is in run standard process in the Linux user space, right? The key things you need to pay attention to here are the two vertical bars, the red and the purple ones. These are the P50 latency and the P99 latency. And we'll see how they change as we apply some of these optimizations. With simple bypass, that is skipping the entry-exit code and going directly to the kernel disambiguation for read and write, we get about 10% on both P50 and P90, right? So we move both bars to the left and we squeeze them a little bit together, so it's a little bit tighter. But the real key here is when we call the TCP layer directly, we get a huge savings. We see 23% better on P50 and 22% better on P99 latencies, just by allowing a user process to interact directly with the underlying networking hardware. Cool. Thanks for coming to the presentation. So the paper will be available with URSys 2023, and there's a poster session out at the first poster second here if you want to come have a deeper look.
I know it looks like a stressed out PhD student going to talk about his best idea ever about a global problem. But I promise you it's not like that. In addition to our brilliant idea about global storage, I'm going to talk about how MOC motivated and enabled storage research by collaborators of different universities and institutes, including BU, Northeastern, Tufts, IBM, Red Hat, Dell, Intel, Two Sigma, State Street, us, and so on and so forth. So I'm going to talk about the research that we have been doing, and Matt is going to talk about the work that is going on to upstream. So everybody is talking about MGHPCC, but for us as a storage researchers, it looks like this. We have NESI, Northeast Storage Exchange, that is based on self-storage and serves a 3 requests through Rados Gateway and push all this through RDB or Rados Cloud Device. In MOC, we found that hard disk, low-speed hard disk that is used by NESI or other high-capacity storage systems, in addition to highly oversubscribed networks, results into low-performance storage. So this is the story of our over half a decade research to serve most of IO requests using local SSDs instead of back-end low-performance storage. Our first effort was to create multiple RGWs with integrated SSD read cache and then distribute this all across the data center. We call this distributed data delivery network or DTN. In DTN, these requests are automatically served by local SSDs. The key idea or interesting research idea here was to develop a two-level read cache. The first layer was local SSD, and the second layer is distributed. By consistent hashing, we were able to enable aggregated SSDs of RGWs to be used as a read cache and therefore reduce the load on the backend. So this graph shows 10 hours workload of a Facebook trace. In the realistic case, we see that DTN is reducing the runtime by a factor of 3. As Matthew discussed, DTN is already upstream in the Ceph code. With DTN, all the writes requests are going to hard disk backend storage. Our next project, D4N, introduces a write tier. We install Ceph OSDs on SSDs distributed on RGWs and modify RGWs to write objects first to these local SSDs, and then when the objects are old enough, we write them back to backend. Since we are using production code, we are giving the same guarantees, availability, and fault tolerance as the production storage. And so for the user, this is just backend like NESI, but with much faster performance. As I said earlier, each VM had a simple caching policy. First local SSD, then distributed second layer. But for D4N, we have this possibility of having more complex caching policies. D4N has a distributed directory, which shows where is the data in the right layer or in the backend. By using this directory, we can have and compare global value of objects instead of local value. Another caching policy that we can use or we developed is write files. By balancing a small writes to 32 megabyte objects, we reduce this utilization. Here, small numbers are better. And as you can see, we never pass, with file sprites, never pass 20% this utilization. The next project was CARIS. CARIS talks to an Ansible framework's scheduler and gets the job stacks from. The job stack shows what tasks are going to be run and what data is going to be accessed. So it knows the future. By getting this information and using this information, we can pin a data in the different directory to prevent its eviction or fetch it into the cache when it's going to be accessed in the future. One important thing about RAs is that it uses a cache space, valuable cache space efficiently because it just caches objects that are in DAG's critical path instead of all the objects that are accessed. This is the graph that shows a TPCH benchmark running on Spark. Green boxes are CARIs compared to MRD and CP, and the two state-of-the-art works. Until now, I have talked about only object storage. What about file system or virtual disks? We want our data center storage to be used by all the systems. Our next project is LSVD, which is about increasing the performance of virtual disks. Here, we accumulate all the writes in the local SSD and then group them as S3 objects and then write them back to object storage. Here is an experiment comparing LSVD to RVD. In standard RVD, as we ramp up the number of virtual disks from 1 to 32, this utilization of the backend rapidly goes from 10% to 70%. The problem is that we have to write data, metadata, get ag. A lot of small writes are happening, which results in 12 times a write application. With our LSVD, while this utilization is 1/5 of the load of the backend, we reach higher IOPS compared to standard LSVD. So let's go back to our single data center storage with read-write cache, directory, and CARIs. With developing an S3 zipper layer on RGW code, we are able to connect our storage to NESI through S3 protocol. We also are able to deploy our storage system into open storage networks nodes or OSN nodes. And an OSN node can connect to NESI and other OSN nodes through S3. We also use S3 to connect to other public, other storages like public storage, such as IBM object storage. Or we can connect to other storage services that provide different types of storage devices, such as tape that are getting popular. So we are here in the beginning of the path to global storage. Remember I told about my our brilliant idea about global storage? So we are here. So our open research questions we have is that where is the data in a global setting? What about consistency, sharing, or security? What about network bandwidth limitation or other bottlenecks? Matt is going to talk about upstreaming all the projects that I know.
I'll play a date. Okay, I promise this is going to be the small end of the talk. Possibly not the negative 2 minutes that I'm paying. But this is me, and I've been fortunate enough to work since about 2017 with a great group of very creative PhD students and research advisors as part of this, as part of collaboration. are around object storage, which is a piece of the puzzle that we've been discussing there. And in the course of this, all the research projects we already described, the students, researchers had to essentially inject themselves into the spaghetti or well-organized but modular code inside of our software in ways that were not anticipated by the authors. And nevertheless managed to rewrite parts of the appropriate parts of our software and enable different kinds of optimizations and redirections. The highway work that my team is doing inside it, formerly it was Red Hat, now I'm part of IBM, and my team members are continuing in more or less the same jobs. We are very interested in capitalizing on the value that is produced in D3N, especially D4N. And some of the ways we're planning on doing that is by incorporating a unified and flexible architecture for our software that allows construction of stackable back-end storage targets, which means that the different kinds of backing for our S3, whether it's the Ceph S3 cluster or whether it is S3 in a cloud or some other place, is easily organized. We are also extending some of the capabilities of S3 in new ways. We're primarily interested in workload acceleration and this sort of effective development. Things like Spark and other technologies that are researched as part of D4N especially. We're incorporating D4N as parts of as flexible layers and doing this stack we call Zipper. We are also flexing the cache hierarchy so that we can design different kinds of caching strategies that use different backing store as appropriate and apply them to more kinds of deployments of Ceph than the ones that D4N was originally targeting. We're also adding new protocols in addition to S3 itself. We are incorporating Quick, ASP Quick variant of S3, and we're also incorporating Apache Aeroflight as a completely distinct low latency object protocol, and we hope to support Flight SQL to enable a query acceleration by frameworks like Trino, ResentDB, and Spark. We already have S3 Select, which is a simplified hands-on query offload mechanism for S3. I'll skip more of this, and I've talked a lot about that. I want to thank the people that allowed us to, myself and members of my team, to work with the best of collaboration, and I wanted to thank my team members, especially Ali Moradia, who's here, for being with us on this entire journey. Anyways, thanks very much.
All right, thank you very much. My name is Manuel Egele. I'll be talking about some fuzzing work that we've done over the last year. And while I'm up here, so I'm the one that italicized the font up there, really the bold font is on my student. All the work that I'm presenting has been done by Alexander Bulikov, who really should be giving this talk, but he's on an internship at EPFL, so across the ocean, kind of far for this event. All right, we'll change things up and talk about security. You might wonder, what do I care about security? Anyone using gas in their car? No one? Great, everyone's driving electric. For those of you who have gas, anyone remember Colonial Pipeline? Well, that one got hacked and then caused a bit of a ripple in gas delivery across the eastern border of the United States. Anyone running Qemu in the cloud? Anyone running any private cloud will most likely be running Qemu or the Ember for whatever reason. When you're running cloud, you're probably concerned about hypervisor escapes, such as Venom. Anyone using Linux? Great, now I get a lot of hands. When you're running Linux, you're often concerned about security vulnerabilities that give you privilege escalation, such as Dirty Cow. And so today I'll talk about the last two things, your gas problem, buy an electric car, and then you're done with that. All right, so from a security standpoint, what we really want to do to make these things less annoying, these things being securities, vulnerabilities, and bugs, is to find those bugs and fix them before the bad guys do. That's good posture. It's also good for finances, because Microsoft says that for any public bug that they have to report, they're spending on the order of $1 million. So whenever they have to do a security advisory, it costs them a ton of money. Better not have those. Nowadays, the most prolific way to find those bugs is by using a technique called fuzzing. So what is this fuzzing business? At the end of the day, we take a system under test, be that your hypervisor, your Linux kernel, your programs, you name it, and give those systems under test random inputs, and then you observe how those systems behave. And so I bold-faced here inputs, because what this talk is about how we actually make inputs that are useful to fuzz hypervisors and operating systems kernels. Once you have this capability, you repeat. You repeat thousands of times per second, and you repeat this for a CPU decades. And you don't do it on your own infrastructure, you have someone else pay for it. We'll get to that at the end. So some examples is why fuzzing is successful. It turns out that Microsoft engineers were complaining about how good their Sage fuzzer was. It reported way too many bugs for them ever to be able to fix it. So that was a good start. And Google's open source fuzzing framework right now supports over 850 open source projects. They found over 28,000 bugs, over 9,000 vulnerabilities in the last 6 or 7 years alone. So really successful in teasing out those bugs and vulnerabilities. As I promised, I'll talk about inputs, because it turns out that giving inputs to your programs, for some programs, those inputs are simple. So you might see programs that consume image files, PNGs, JPEGs. Those inputs are fairly straightforward, so you can almost literally go with random. However, if you have other programs, such as a PDF reader, where all of a sudden you have a lot of structure to your input files, or you have hypervisors, or you have operating system kernels and their system call boundary, your arguments or inputs become now very challenging to deal with, and this arises essentially from the semantics that is imposed on the data for those inputs. So how do we deal with challenging inputs? Historically, what has been done is that someone sits down, manually writes a grammar, and then we draw inputs at random from that grammar, rather than truly random inputs. That's great. It's a lot of manual work to develop those grammars and also hide some of the bugs. What we did instead is we reshaped the input space so that we can take truly random information and just provide it in the correct form. And we can do this by essentially observing how inputs are being consumed by the systems under test, and then have transformers that morph random inputs such that can be consumed by the systems under test correctly. So how are those inputs consumed? We'll have two quick examples. One is on system calls for the Linux kernel, and one is for the hypervisors. So the Linux kernel, fortunately, cannot reach out to user space directly. It will consume information from user space either via registers during a system call, or use get user or copy from user to access user space information. So by realizing that, we can simply put random information at the correct places and then use traditional fuzzers to tease out new bugs and vulnerabilities in the Linux kernel. So this is fresh off the presses. Alex gave the presentation on this paper earlier this month in San Diego. Here's a little overview of how it works. Don't worry, I won't stab through it. Really, the takeaway is, historically, we have these grammars, so 33 pages that cover only the KVM subsystem in the Linux kernel. What we get with our system is essentially 7 lines of configuration, finding more bugs and bugs in code that has already been covered by previous fuzzers. Yeah, let's skip the detailed results here. So in total, we found 9 new bugs, including 5 bugs in code that already has been fuzzed by the industry standard syscaller fuzzer. Now switching gears, talking about how we can fuzz hypervisors with exactly the same technique, right? You realize the salient points of how the system under test consumes inputs, and then we morph truly random inputs to the corresponding input channels for the systems under test. So what we did for virtual devices was exactly the same thing. We realized those input channels. There are 3 for virtual devices, just on a physical machine as well, at least on an x86 machine. We have port I/O, memory mapped I/O, and direct memory access. If you look at how complicated it is to deal with those things, Port I/O is pretty simple. Memory mapped I/O is a little bit harder, but still pretty simple. And then when you're trying to deal with DMA, all hell breaks loose. Nonetheless, we also put that into production. We wrote a paper on it that was published last year at Usenix Security. And again, all the work was done by Alex. Here we have a little overview of how the system works. Again, not going into the detail. If you're intrigued, please read our paper, hit me up in the break, and I'm more than happy to talk about it. The core idea that we have here for this paper was essentially to take all these dispersed memory areas and funnel them together into one consistent memory area that can be easily fuzzed by a fuzzer. So how was that evaluated, and what are the results from that? We fuzzed 33 virtual devices, many of which are enabled by default when you're running QEMU, so most of your clouds will run this. We found 66 new bugs, and we found whatever is left to the 110 from bugs that were discovered by previous work already. Buffer overflows, use after free, the whole garden variety of your security class is part of this paper. We found them all. We found all the flavors, not all the bugs. Just want to make sure I'm not saying something wrong here. So yeah, these are the research outcomes. I wanted to spend the last few minutes of my presentation to talk about outcomes from our research that are not purely on a basic research angle. So in the previous talk we heard that there are efforts ongoing to upstream research prototypes into open source projects, and that's exactly what Alex did as well, because he's not content with just writing papers, he's also making his software useful for everyone on the planet to use it. And so our Morphos fuzzer is a part of QEMU in the main branch, so if you download QEMU today, you'll have Alex's code on your system. Furthermore, Alex managed to get QEMU, the open source project, accepted at Google's OSS fuzz infrastructure. This is very nice because now Google provides the resources to continuously run our project on thousands of CPUs, day in, day out, 24/7, right? So all the code is on GitHub, of course. Here we have the screenshot that shows that QEMU is actually part of OSS fuzz, and the last commit, as you can see, is also done by Alex. I took this screenshot yesterday, so it's fairly up to date. So Morphos is an open source fuzz. That's great for security purposes. Now, if you are a developer contributing code to QEMU, you might not like Morphos as much as the security people do. Because let's say you're writing a new backend for QEMU, like the Intel Gigabit Ethernet networking support for the E1000E device. You get your code admitted into the QEMU repository, you're all happy, and the next thing you know, you get an email from the automated system at OSS Fuzz that says, oops, you made a bug. So that's what our infrastructure is currently doing. It will check whatever the commits are that go into QEMU to find bugs, hopefully before the bad guys find them and can exploit them. So in summary, instead of sitting down and manually writing grammars, what we do is we reshape input spaces so that we can give random inputs to systems under test that consume complex inputs. And the goal is to find bugs and vulnerabilities before the bad guys do, and therefore make systems more secure. At the end of the day, we have the papers to back it up, we have the systems to back it up, we made your clouds more secure, so you're welcome.
I'll take less than a minute of your time and give some context for Hans' work before I turn it over to him. So as most of you probably know, energy efficiency, which is the amount of computational work done per unit of energy consumed, is only going to be more important as time goes on. Now, energy efficiency can be approached at many levels. At the lowest level, chip manufacturers put in various mechanisms at the processor level to enable energy savings when the processor is idling. And on the other end of the scale, there are various strategies at the data center level. Now, while research in all this is always going on, it would be desirable to exploit existing mechanisms and well-written software to get energy savings. And Han's work focuses on such as software-driven mechanism or network-heavy workloads, where, as he'll show soon, you can use two mechanisms, batching or grouping of incoming work or incoming requests, and a processor-level energy-saving mechanism to get substantial energy savings in realistic workloads on Linux without sacrificing performance or while satisfying SLAs, service level agreements. And our hope and our goal is to now extend this work to distributed environments like OpenShift, where there's a lot more stochasticity in the environment. So with that, I'll hand it over to Han, who, by the way, recently defended his PhD thesis and is actively interviewing and on the job market. So if you want someone who's technically excellent and very creative, you should really talk to him.
All right. So this project is actually part of a much larger project about trying to understand how and performance in operating systems and how setting configurations in the kernel and the hardware can impact it. So kind of this work is just a small part of the project. So kind of like in our operating system these days, there are these many kind of dynamic policies that these device runners have written or the kernel developers have written. And sometimes they don't really talk to each other in terms of trying to work towards some common consensus energy efficiency. And kind of our work is more trying to exploit two of these mechanisms that are currently being set by some sort of dynamic policy and try to set them in a more intelligent way towards a very specific application. In this case, I'm just kind of focused on American heat value stores or heat, and kind of trying to improve the energy efficiency here. And kind of we want to do this in a way that we kind of remove kind of our existing mechanisms that kind of fits in a way that's more broader class. We want to focus in a way and use mechanisms such as machine learning tools to do that, to make those decisions for us. So at a high level, the two mechanisms we're going to be using is this mechanism called interrupt coalescing. It's a very common mechanism on network devices, where it basically sets a time limit where the interrupt decides to decides whether the software network that they updated the process. And then the other one is also a common one, which is this dynamic voltage frequency scaling. It's a common mechanism on processors to turn down their clock speeds to save energy, but your application is going to run longer, right? The clock is spinning slower. So at a high level, this is kind of a mental picture for how you want to think about this, right? So you're running some sort of network workload, and packets are coming in on the network buffer, and at some point, that's when the interrupt coalescing mechanism comes in, right? You set it to some sort of particular value, and after that particular value has been hit, when the hardware figures that out, it's going to fire an interrupt. And when the hardware fires an interrupt, you as the software are going to have to handle that interrupt. So you're going to start reading off the bytes that are currently on the buffer, and then pass them up through the network stack, and then eventually to the network application itself, where the network application will then process it, right? So this is what we call batching in these cases. And then the second component is something that we call DBFS. So this DBFS mechanism comes into play really in the software side, which is when the network stack is processing the application and eventually the software, how fast do you want to process it, right? As you lower this DBFS clock, you're processing the application instructions slower, but at the same time you're saving energy. Because part of that process is that you start shutting off parts of the ALU's example of the processor itself. And kind of the key insight that we found from this work is actually there's this interplay between these two mechanisms, right? Because the interrupt delay sets up these fixed batches of work that you can then pass on to the processor to process. And that's when the DBFS mechanism comes in, because then you can better figure out what is the right speed to set the processor to then process this batch of work. So you can set this in a very fixed and lockstep way that has very interesting system behavior. And kind of the way we approach this is we built this entire data gathering infrastructure in Linux, right? And we instrumented this to collect a bunch of fine-grained logs, such as where every time a neuron gets fired, we collect a bunch of statistics, and we collect this across multiple cores, across multiple applications, and across multiple OSs other than Linux. And we have this whole data set that we built to better understand this mechanism initially. And then after that's been done, we collect a bunch of data. So basically, we explored up to 340 combinations of these two values, the intercoalescent and the BFS, as well as a bunch of data that we collected. And kind of the figure on the right that you see, every single dot is a single experiment that we ran. I wouldn't focus too much on kind of figuring out what exactly is going on, but I want you to pay attention to kind of the general structure that we see, right? You see a very distinct structure across these multiple applications, and to us that spoke to us in terms of, oh, maybe we could then let some sort of intelligent agent to set these values such that you can figure out where to trade off the performance and energy within these curves. And getting to that, so a kind of motivating use case that we saw that we could then apply these two mechanisms are kind of like in-memory key value stores. So the figures here are actually figures released by a bunch of these companies like Facebook, Twitter, and Netflix, where they show the utilization of their in-memory key value stores. So one thing you might notice when you examine these graphs is that these exhibit a very similar structure, as it changes very slowly over multiple hours across multiple days. And also the request rates change very slowly. So this spoke to us as an opportunity where we could do some sort of coarse grain optimization on some mean request rate over multiple days. And could we get a system to actually automatically figure out a way to use lower energy? So the problem set that we built was, given a single machine, could we then figure out that how can we build a controller, which is the machine learning side of things, to then, from the outside, set these two variables in a way that will meet the SLA. So in this case, for MacFC, they usually define service levels agreement that says something like, let's say I want 99% tail latency under some set microseconds or milliseconds. And kind of that's what this machine learning agent is doing is that the exterior of this node is basically querying the node itself to figure out are you currently hitting your SLA and can I lower your energy further? And as we move on from the experimental side to a more practical side, there's actually 2 million different possible configurations of this IGF BFS value. We only did 350 for the experimental side because we just wanted to finish running the experiments. It's the first time. But if you actually set the entire space, it's about 2 million different numbers. And that kind of leads into our experiment here. So the figure on the blue, the top one, so that's kind of current limits that we use with this dynamic policies. And then on the right is the changing GPS rates over a full 24 hours. And then the green line that we call Linux layout is when we apply this machine learning technique called agent optimization to it, where it automatically sets this machine to use less energy, but at a particular SLA objective. So there's a lot of interesting things going on in this class in terms of you see spicy energy use and sometimes it settles. And after this, there's a poster session, so I have more results there. If you're interested to talk about it more. We also have, and then we found that this agent can actually do this kind of SLA. You can actually target towards multiple SLA objectives. So there's a lot of flexibility there in terms of figuring out what is your performance and energy trade-off. Yeah, so that's it for me. Thank you.
Please navigate back.
You should be here.
I know it's actually moved somewhere.
We moved it.
Oh, you did? Oh, perfect.
His fault, he put his talk in the wrong spot.
Right there. So just so you all know, we realized the grounding situation in the last spot before lunch, and people not to understand putting people under. So we'll be quick. Afternoon, folks. My name is Ahmed Sanalla. I am part of the research team at Red Hat, and presenting with me today is Sahan Madara, who is a PhD student at Boston University. So we've heard this morning, specialized hardware is absolutely wonderful. It's great, it's amazing, it allows us to do our workloads with a lot of efficiency. We're able to do stuff, we're able to do more stuff within our power and hardware budgets, or we're able to do the same amount of work but with a smaller budget. The challenge with specialized hardware is that it's difficult to program and use effectively. I mean, if you look at the software development flow, it's so extremely efficient because you have, platform agnostic software running on top of the general purpose OS, running on top of general purpose hardware. So there's a lot of reusability, there's a lot of guarantees, things you're able to sort of focus it on part of the stack and do research, innovation, or product design over there. And everything else works reasonably well. But if you contrast that with the hardware development flow, specifically specialized hardware, not so simple. I mean, you're looking at way more layers in the stack, and you're having to customize at multiple points just to really leverage that flexibility that the stack offers and to get that performance and power efficiency out of it. But there's a way to solve that. There's a way to sort of bridge the gap between the development flow of specialized hardware and bring it closer to how streamlined software development flow is, and that's through hardware software co-design. It's really nothing too complicated. It's not like a magic pill. It really just says that hardware traditionally has worked for niche applications, but now there's actually a lot more workloads that will benefit from it. So we should look to design hardware with the interfaces and abstractions that allow software to leverage it. And software typically has been designed to run on these general purpose stacks, but now we should be looking to develop software with the assumption that perhaps at some point we will need to leverage non-traditional hardware in order to get that efficiency for our workloads. And so CODES, which stands for co-design, great name. For a lot of effort. Anyway, so the CODES lab is located on the 12th floor of the CDS building. It's an on-premise research lab which advances specialized hardware projects, with co-design being sort of this core part of that, core focal point to that research. What it isn't is a replacement for these shared infrastructures that we have, because it is more like an on-premise incubation step, because the current infrastructure that we have, the support for them is really not there. And when I talk about support, I'm talking about very low-level system support, like network controllers and PCI controllers and memory controllers. But we need that support to do the research, and we need to do the research to, bring the support up to par. And so that's where CODES comes in, is that on-premise incubation step that allows us to start the projects, get them to a state of readiness and completeness, stability, and then transition them into the larger infrastructures, whether it's at the cloud or the edge, and then continue that research as needed. And so, there's a lot of benefits to doing this stuff on premise. We have more control over the hardware, because we're not looking to just do FPGAs, it's FPGAs, DPUs, microcontrollers, all that wonderful stuff. More control of the software. It allows us to try out these non-typical, deployment configurations, and this collaboration. And the most important part is, again, this is not supposed to be a replacement for the existing large infrastructure, but rather sort of that step towards deploying stuff over there. So there's one research project going on that actually exemplifies this really well, why we need something like this, and that's actually the Sahan's research project. So I'm going to hand it over to him to talk more about it.
Thanks, Evan. So I'm going to give the perspective of a user of the co-design lab and tell you how my research benefits from it. But before that, let me start off with a real example of the type of research enabled by this. So this is what the host FPGA communication looks like for an FPGA attached to a server. The host is running some custom driver to support the ACI communication, which is specific to this FPGA device because the file and the vendor provided IP core differs from one vendor to another and even from one device family to another. So there's a lot of device-specific data which needs to be captured by this driver. Unfortunately, there's not a lot of support there's not a lot of upstream support in maintaining these drivers. However, if we can use standard internal drivers like Vertigo, we can remove a lot of this overhead by the overhead of maintaining these drivers. So what we did is implementing a Vertigo compliant interface on the FPGA itself, so that we can use unmodified Vertigo drivers to communicate with the FPGA. Because the Vertigo driver does not differentiate between a physical device and an emulated device, this opens up a lot of new use models, and you can see that it's very handy to have this deployed in a large infrastructure, because you don't have to maintain a whole lot of drivers with these different devices. So this is just my FPGA showing how as a Vertigo console device. These are the PCI devices. But to get there, so doing this research, it has its own set of challenges which make it difficult to use shared infrastructure to do this research. So, for instance, in this particular research, implementing a Vertigo compliant interface on the FPGA means configuring the PCI controller on the FPGA in a very particular way, which is not something you can do easily on a cloud FPGA, because a cloud FPGA usually runs with the FPGA shell, and the user does not usually get to play around with that shell and PCI controller. So essentially, you need bare metal access to the FPGA. Let's say we got that. Because you are configuring the PCI controller and you configure it incorrectly, that does not simply disrupt the host FPGA communication, it can crash the host server as well. So now you can't do this research on a shared server. So you have to have a whole node allocated just for yourself. Let's say you got that as well. When this host machine crashes, sometimes the only way to recover from that is to fully power cycle. So now you need access to whatever the remote power cycle mechanism of that server. So you can see how this increasingly gets more annoying for systems admin, me asking for all these low-level permissions. And this is just for this project. We do not know what level of level of access we will need for the next project. So that's why it's very beneficial to have this on-premise infrastructure to carry out this research until it gets to a point where it's stable enough to transition into this larger infrastructure. So the next obvious question is, why don't you just buy your own machine to do this research? So the problem there is there's multiple research efforts going on at the same time. Not all of those are ready to be integrated together at the same time. So if each of the components were developed on different hardware software stacks, there's going to be a lot of overhead when we are trying to integrate these together at the end. So code has helped us prevent these research efforts from becoming these one-off implementations which are not compatible with a real-world system, but gives us this incubation step where we can bring our projects to a certain level so that we can safely transition them to wider cloud infrastructure for the next steps. Thank you.
Okay, I just have a couple of announcements before we go to our lunch. First of all, we obviously had a very, very full program this morning, so there was not a lot of time for questions. So many of our micro talks will have posters next door during our lunch in the small ballroom. So please take the time just to go by and see the posters and get all of your questions answered. There will also be two birds of a feather happening during the lunchtime. There's one on ESI at 1:15 to 1:45 or in room 315. And the conference rooms are up the stairs and through the doors to the left or to the right. And then there's a second one I need my glasses, federated authentication, and that is going to be next to the NERC poster during the poster session. So that's going to be going on throughout the poster session. Also, for those of you who are in the Open Cloud Testbed Advisory meeting, please gather your lunch, and the meeting will be in room 310 upstairs. And lunch will be served in the terrace room, which is through the lounge and down the hall to the terrace room. That's where lunch is. And then there's a lounge here. You can have your lunch, or you come back here to the ballroom. And of course, please see our poster sessions. And if anybody does have any dietary restrictions, please see Tara, because she can guide you to the appropriate tables. Okay? Enjoy your lunch, and we are back here at, what time are we back here? At 2:45. Thank you.
I just wanted you to say a couple words and just use actually being Red Hat research, worldwide Red Hat research. And he's been my partner in crime on Red Hat Collaboratory and co-director of Red Hat Collaboratory. And in a lot of ways, while the MOC Alliance is centered at EU, I think it's as much collaboration with, it's a multi-institutional effort as the EU is also very much collaboration with Red Hat research. So, you know, just wouldn't have accomplished anywhere near what's being accomplished. And the funding of the research that's gone around this has really been the value that the Red Hat's been so involved in. And beyond the research funding, the biggest thing has actually been the engagement of engineers with researchers, being able to solve problems that we never could have solved without that kind of involvement. So, thank you, and
okay. I'm going to use the mic so you guys can hear me. So our next speaker is Blake Schreiber. He is Red Hat's VP of Cloud Partners, and I'm very, very happy to have him here today. The reason I asked him to be here was because of our whole involvement with the Mass Open Cloud and to some extent with Boston University and research here is based on the idea of an open collaboration among universities and industry partners grounded in open source. So the partner aspect is really, really important, and Blake is going to come, he's going to talk about the different ways we work with partners at Red Hat, the things that we have got out of working here with the MOC, with Boston University, and how that can all tie together, and hopefully how some of you folks who are industry partners in the audience can jump in and help, because that's what we're really after is more. So without further ado, Blake Schreiber, thank you.
Wow, I feel like I lost the audience. Everybody went to lunch and didn't come back. If anybody can hear me out there, you don't want to miss this, I promise. It's okay, I'll tell a good joke and everybody will come on. Okay, so I do this. Oh, look at that, it works. Well, I hope everybody had a good lunch. As Hugh said, my name is Blake Schreiber. I lead Global Cloud Partner Business at Red Hat. I'm a lifelong advocate of open source collaboration, and so given the collaborative moxie in this room right now, what I've experienced so far, I consider it an absolute blessing to be able to speak to you all today. So from what I understand, I've got three main groups of people in the audience today. There's research leaders, a couple of business leaders, maybe guys and gals in the jackets, and students who are our future research and business leaders and who've just done an outstanding, impressive job talking about their projects today. In my life, I've been a student, I've been a researcher, and for a short period of time, and currently I'm a business leader. I studied computer science in college, which was less than 20 years ago, yet that education is so out of date it's not even funny. I studied the cloud had not been officially coined when I graduated from college. However, while in graduate school at Clemson, I read an article about a guy at Google who had termed this new concept of cloud computing. That was about 15 years ago, I think. I knew at the time that this new idea had massive potential, but I would never have guessed that I'd end up spending my entire career with the cloud being a primary focal of what I do. Yet here I stand 15 years later talking about the cloud to all of you. I hope that by the end of my short talk today, I will be able to bring a little more clarity and awareness to each of you in the room today. For the researchers in the audience, I hope to be able to show you that with Red Hat, you can bridge the work you need to do directly on bare metal hardware with the increasing capabilities that are evolving on hyperscalers and cloud providers. For business leaders, I hope to be able to demonstrate that Red Hat is an industry leader in enabling the hybrid cloud, which means we can enable cutting-edge technology and connect an entire ecosystem of partners to that world of innovation. And for the students here, which I don't see a whole ton of, but this might be the most important group here, I hope you'll see that you have access to the tools that will serve you in your educational and academic pursuits today and into your career for the foreseeable future. So just to start off real quick, I want to talk a little bit about our hybrid cloud strategy. About a decade ago, the idea of the cloud was emerging, as I mentioned before, and at that time, most people thought we'd see two paradigms. We'd see public clouds and we'd see private clouds, and everybody would just go to one of those two. The reality that emerged is a world where compute workloads can happen on physical bare metal and virtual clouds with total abstraction. That's the world we live in today. And while there are a dozen or so hyperscale cloud providers, there are hundreds of cloud providers across the world that address specific market needs. For example, data sovereignty requirements that limit where data can physically be stored have spurred markets for many cloud providers globally. There are hundreds of managed service providers who have majored in creating industry-leading cloud services to support very specific industry needs, which can differ wildly from financial services to airlines to oil and gas and so on. So while it seems to be a concentrated market around a few global cloud providers, it's truly a very diverse and robust market ecosystem with an unthinkable number of permutations of combinations and solutions. Very early on in our journey, Red Hat saw that many customers would really thrive in the cloud if they had ultimate flexibility and choice in how, when, and where they deployed their compute workloads. Having the flexibility to deploy on bare metal servers, virtual machines, private and public clouds, and even specific hardware running at the edge of a network is highly valuable. Then couple that with the choice to run these workloads across cloud providers with seamless abstraction, and you have a truly liberated and robust hybrid cloud experience. The relentless pursuit of this ubiquity and flexibility is what drives Red Hat every day. This is Red Hat's open hybrid cloud strategy and vision. Allow innovators to move fast on stable, enterprise-grade platforms and scale without limitations while maintaining flexibility and choice at all phases. But why is this so important to us? Red Hat really is more than a business. We're a collection of people who want to change the world. To steal a line from Jim Whitehurst and the Blues Brothers, we're on a mission from God. We see the world-changing technologies that can be designed, built, and deployed in an open hybrid cloud framework, and the possibilities are endless. It's hard to imagine being comfortable in a car that is driving itself, but this technology exists and is already at some level a part of most of the cars driving out there on I-95 right now. The innovation in this space is happening faster than most of us could have ever imagined. But at the end of the day, you, the driver, have to adopt the technology if it's going to go anywhere. You have to feel safe loading your family into a machine and trusting that machine to safely navigate the chaos of driving and deliver you to your destination alive. There's no room for error, and so the platforms that run this technology have to be the best in the world. They have to start up every time, never crash, and maintain astronomical security standards. They have to work on bare metal, edge hardware, and communicate with the cloud. They have to perform better than you, the person that loves the people in the car more than anything, in order to gain your trust. Now, I'm a sales guy, and I can tell you right now that that is a very hard pitch to make. But it is coming, and every single one of us will confront that decision in the next decade. So take all of this context and then back up to the day the first part of the code for this self-driving car is typed. How much integrity is gained in that process from the spark of innovation to the trials in the test lab to the moment the family is loading up in that car for a road trip? If the platform used to build, test, and deploy was one consistent, industry-leading platform from start to finish. This is an example of ultimately what has to happen to enable the rapid build and scale out of application that is going to change the lives of tens of millions of users. This is what allows companies to stake the entire future of their in-car OS vision on one stable, secure, and scalable platform. Soup to nuts, this is the applied value of Red Hat's open hybrid cloud platform. Providing world-class software to enable hybrid cloud infrastructure is awesome, but without a diverse and integrated set of ecosystem partners, we would not be able to unlock the world's full potential with these tools. Our goal is to meet our end users and customers with the technology to change the world in any type of physical or virtual environment. And the experience we enable between the two should be seamless and smooth. It truly takes a village to do this, and the community at Mass Open Cloud and Red Hat have been working to build that village around open source technology. As the needs of our customers and end users continue to evolve, we also evolve our technology and business models to continue to meet the highest of expectations. In fact, the entire ecosystem Red Hat brings to the table eclipses 6,000 partners worldwide. In the cloud partner space alone, which is what I look after, we work with over 1,400 partners to advance the vision of open hybrid cloud together. This is a massive feat, but this ensures that the world-changing technology is not limited to a small set of vendors or groups. And this is really the spirit of open source in action in the business community, working hard to ensure availability across ecosystems and technology partners. So what do we do with all of this? One project or one new piece of software or even Red Hat alone won't modernize the cockpit of a commercial aircraft. This is where we come together with our partner ecosystem and the innovators who are developing cutting-edge software-defined aviation technology. When we bring the pieces together, at that moment we breathe life into a new integrated technology solution. Red Hat does not make the flight control systems that you see in this screen, but many of our partners do. And when you need a trusted platform that can seamlessly operate on these specialized hardware systems at the far edge of a network, and also communicate with the connected clouds and on-premise data centers back at home base, this is where Red Hat shines. We have to be that platform, but we also have to connect these partners and innovators together in unique ways to bring new ideas to life. When I look at a project like DISL, which from my notes is Dynamic Infrastructure Services Layer for Reconfigurable Hardware, I see tons of potential here. Here in this room we have, I think, members of the DISL team. Somebody, DISL team here? Still at lunch? And I believe some people from the Air Force as well. I was told Air Force might be in the room too.
They're online.
Awesome, Air Force is online. So it's a long shot, but if we could get the Air Force here for cocktail hour and the DISL team back in the room, it would be a super fun cocktail party topic for tonight on how the Air Force, DISL, and Red Hat can change the cockpit of an airplane forever. This is just a fun example of how the research that is happening right here in this collaboration can be applied to enable the airplane in this picture to one day fly itself. So here's my shameless pitch slide for the business partners in the room today. Red Hat seeks to unlock transformative capabilities for our customers. And when we really think about what is required to do that, we need an incredible partner ecosystem to make that happen. Hence our motto, customer first, partner always. For everyone else in the room, it means Red Hat is going to work everywhere on every hardware platform. Red Hat will also work across physical and virtual environments, which you're probably tired of hearing me say at this point. We're not a point solution, we're a technology platform that enables unimaginable innovation to succeed. And there are critical points of value at every step along the way. The key thing to take away here is that Red Hat is a connector that creates ecosystem value. And by being that connector, we can be more effective together as a whole at bringing open hybrid cloud capabilities to the world. Now students, or if there's any students in here, a couple, I want to talk to each of you for a minute. You face a very important choice when you decide what software tools and platforms you will innovate on. During my time in grad school, a long time ago, I remember choosing to major in R, which is an incredibly useful open source tool. But I found myself having to learn new skills and new tools after I left school. All the work I had done to innovate super cool algorithms that could compute non-parametric statistical estimators would not easily translate to the platforms that my employer made available to me. To some degree, I felt like my work was lost. Nowadays, I realize things are different, and there's a lot more portability and integration against software tools than ever before. And honestly, I expect that trend will only continue to improve over time. But choosing to use Red Hat as a platform to build your research on is a choice that will serve you today and into the future. We are constantly innovating and evolving and bringing the best of open source to your laptop, or the server running under your desk that eats your feet in the winter, or the high availability cloud instance that you are deploying to. Or even the quantum computer that you might be trying to use to access the potential of parallel universes and take your AI project to the level of the unimaginable. And that's just something to consider, AI for Cloud Ops team, if you're still in the room. Talking about this bridge to quantum computers may seem like science fiction to many of us, but this technology is real, and each of you can even run basic logic on a real quantum computer today. IBM has democratized access to its quantum compute research lab through the cloud. thus officially creating the most far-out hybrid cloud use case that I have yet to encounter in my life and tenure. The students in this room probably already know this and probably have already executed a teleportation algorithm on a quantum computer by now. And for those of you who haven't, go do it by Friday, and that is your homework assignment. This is the cohort that will change the world we live in. The open hybrid cloud vision not only serves us today, but it fuels and enables successive waves of innovation on technologies that haven't even started to hit mainstream yet. But I also want to highlight problems and technologies that can impact all of us right now today. What about the technology that can help an apiarist better care for her bees and help to stave off the endangerment of pollinators, one of our most precious natural resources? When I hear about research projects like prototyping a distributed, asynchronous workflow for iterative near-term ecological forecasting, I see the potential to save humanity from a crisis of famine if we can just connect the research with the applications through the power of the open hybrid cloud. We rarely know all of the specific applications that a focused research project can have, but when we connect researchers across domains and collaborate like we're doing right here today, sparks fly and the world changes. That is really the true impact and power of this incredible community. Red Hat is here at the MOC Open Cloud Alliance, and we have been here since 2015. We are committed to this environment and platform and the incredible collaboration that is happening in front of us. I am also super excited that our partners are seeing this as a viable open space to work with us. I want to say thank you to some of the partners who are in the room or on the phone, and please forgive me if I leave anybody off. So thank you to A-Star, AMD, AWS, Alibaba Cloud, Ampere Computing, Apple, ARM, Cloudflare, Dell, Flax Computing. Of course, I have to thank IBM, my mother company, JP Morgan, Lenovo, Lightbits Lab, MIT Lincoln Laboratory, MathWorks, Microsoft, NVIDIA, Open Infra Foundation, Peraton Labs, Qualcomm, Seagate, State Street, 2 Sigma, and U.S. Air Force. These are the folks that will help us move mountains. I don't know of any other place where we can really work together with partners in the open and with real customers and users the way we can at MOC Open Cloud. There's tremendous potential here, and I hope that through my short talk today, each of you sees a new way you can amplify the impact of your work with the power of the open hybrid cloud. Thank you.
That was great, but I have to correct it, it was 2014 we started this.
Oh, okay. Maybe it was our fiscal year 2015, which is offset. Thank you.
Were there questions?
Yeah, any questions? I've got a few minutes if there's any questions.
We're really jam-packed.
Yeah.
So I guess the word hybrid I think of as being an enterprise to the public cloud. That's what I think of as hybrid. Is that when I think we're at the end? Oh, sorry, I don't know. When I think of hybrid, I think of hybrid as being enterprise to the public cloud. What's happening here is actually multiple universities, multiple public clouds, enterprises. I actually, it's not just an enterprise to the public cloud. It's actually many, many cross-connected things. Is that what you think of when you say the word hybrid?
When I say the word hybrid and when Red Hat uses the word hybrid, what we really mean is absolute flexibility. It doesn't mean you have to pick one or the other. We hear about a lot of cloud-native companies that have started up, born in the cloud. That's great for those companies, and they have, they will probably remain in the cloud for most of their life. But when we look at a customer like Kohl's, for example, they're not a born in the cloud company, but they've got to adopt to the cloud. They want to create an app that allows their customers to buy stuff online and real-time update the inventory system that might be running in an on-premise data center somewhere. So when we talk about hybrid cloud, we're talking about flexibility, we're talking about choice. And it does tend to angle towards the enterprise customer because that's what Red Hat, focuses a lot on. But that works really well for this group as well too. Maybe not necessarily an enterprise business that's running, but that's looking for some type of flexibility in how you want to work. You may develop a research project on bare metal, but then as it takes off, you want to deploy it on the cloud. I was, really taken away at the project that we looked at earlier that looked at how we can make the compute cycles on a processor almost 40% more efficient just by looking at what is happening and making some I mean, a little bit went over my head, but it was awesome engineering stuff. That right there had to be designed on a bare metal computer, but that could change the entire world if we were able to deploy that on the cloud. And if that project was built on Red Hat, using Red Hat technology, then it is much easier to scale that into the cloud. So that type of flexibility is what we mean when we say hybrid cloud. Question behind you.
Thank you. I have two questions about the research agenda, the research topics that you organize. First is, how much of the innovative research done by your team arises from their understanding and interest in what the cloud can do versus specific requests from clients? And of the requests that emerge from clients, how many are driven by, how many of those are driven purely by desire to be more competitive versus trying to manage new regulatory requirements that they face in government?
That's an excellent question. Thank you for asking that. There's kind of two ways that I think of research happening in Red Hat's world. There's research that we do as part of collaborations like this, and just as part of being in an open source community, to figure out at an engineering level, how do we make sure what we're doing just absolutely runs better than anything else in the world. Then there's the research that we do just by working with a customer to figure out what business problem are they trying to solve, and how can we enable them to solve the business problem. The example I gave about Kohl's earlier, that was a project. It's not as high IQ, but it solved a major problem for them, and it opened up a whole new revenue stream for them. I don't know if this is I don't know exactly what all public customers I can really reference, so I'm staying up here, but I know we had a fast food chain that needed to develop an app for customers to interact and make food orders online, and that was one of the ways they wanted to address business growth during the pandemic. Engaging in that process with them was almost like a research project for us. We put consultants together with them to figure out how do we build that app, how do we deploy that app, how do we make sure that it's always available. If it goes down in one region, we can spin up clusters in another region and make it happen. Through that, requirements are generated that feed into that engineering pipeline as well. So you kind of have those two levels happening. There's also some very cool stuff that we're doing in what we call the edge of our networks. When we talk about the edge, the cockpit that I showed, that's a real example, like self-flying planes, especially drone technology. I'm trying to innovate some autonomous technology there. That's also very research heavy, where we get some requirements from the customer, and then we get together in an open collaboration lab and figure out, all right, how do we make that happen? How do we breathe life into that? And that's a very interesting process. But the way that research happens at Red Hat is more like a community-based model is the best way that I can put it. It's like a community of people coming together to solve a specific problem, and then from that, some type of business opportunity generally is generated.
With respect to the customer request, does it arise often from their need to address a government regulation and then looking for a solution, or not so?
It can, yeah, it absolutely can. In the drone example that I was talking about, there are definitely some government regulation requirements that come from that. Or in financial services, we'll see regulations that will come from that industry. Healthcare is another one. We want to create more data availability or make it easier to share data between different platforms. There's some HIPAA compliance things we have to address there too. So there's definitely some industry-specific, a lot of industry-specific requirements that come from those research projects that then make it into that platform that's then commonly available for everybody to use. So I think that's another really interesting thing about it being, you're not buying a license when you buy Red Hat, you're buying a subscription to everything that we figured out up to that point. So as those new requirements are identified, that just kind of becomes part of what you're getting. But yeah, absolutely. Absolutely, a lot of it is driven by those requirements. Competitive, I mean, I do think that customers are always looking for a competitive edge, but it's more, how do I develop a growth line of business, a new line of business, not how do I do something, better than somebody else. They know that their competitors that are buying Red Hat have access to the same technology at the end of the day. Very great questions, thank you.
Other questions? Well, let me add one more, because I like your statement about hybrid cloud. That's great, but in the sense of being able to run anywhere. But there's a specific use case that we had. Like if you look at Rudolph's talk on Chris, it actually was talking about running things out there, but also about data sets that were shared across hospitals and being able to do analytics across much larger data sets, that collaborative thing. You know, my colleague that's going to come up from 2 Sigma is going to talk about how they use the public cloud, but they have a highly secure requirements, and it's one enterprise working out. But what you talk about Red Hat going in and doing these collaborations, that's part of academic life. We share data. I mean, we compete on publications, of course, but much of what we do is about collaborations across institutional and national boundaries. How do you see that stressing the models that you're thinking about? Or is it just fit in naturally?
I think, well, you know, very good question. I think, first of all, Red Hat's culture is a very community-based culture. Most corporations are hierarchy-based, you know, because that's how decision-making is going to flow very efficiently. Any Red Hatter in the room will certainly laugh when I joke that decision-making doesn't flow very efficiently at Red Hat, because we're just designed more as a community, not as a hierarchy. So when it comes to working in an academic setting or in a research setting or in a problem-solving setting with a customer, we naturally perform very well there. And that's the feedback that I get from our customers and from our partners, you know, for that. So I do think that the way that we're set up, the way that our culture is structured, gives us an advantage that we pass on as we connect customers and partners. Extending that into the, you know, to the world of research, you know, maybe there's probably a lot more that Red Hat can do in that space. I mean, we get into these point engagements and we work on something, we deliver it. But if we were to look at a project, how it affects the world in general, I don't know, we like to think that when we produce something, it's making the world a better place. But a large research project overall, it's one I'd have to ponder, like how do we make that happen better? How do we do more of that? But anyway, I think our model is set up to be very conducive for that type of approach.
Well, I definitely agree with that. Comments or any other questions? All right, let's thank.
Thank you all.
I guess I'll say a couple of words to introduce Larry. So Larry's our principal engineer for the MOC. He's been a long-term he's a distinguished engineer. Okay, so distinguished engineer for the MOC Alliance, and we've been working together for many years on this effort, and I'd like Larry to introduce John.
Thanks, Ron. Yeah, I've been here, I think, at all the workshops you've ever had. I'm working at 2 Sigma. I'm happy to introduce John Stump. He's our head of infrastructure and operations, or whatever the official title is. Before 2 Sigma, he was at Johnson & Johnson and Moody's and AIG. But the real thing that's exciting about him is that he was part of the Olympics and distributing the media for the Olympics, which is another connection to Iran. But I also just want to say a little bit about 2 Sigma, that it's a high-tech trading company, and the modelers are the thing that makes us money. And the modelers just want more computers and more data. Don't change anything else. Just give us more computers and more data, and keep doing that. And John's job is to keep things not only running, but knowing that, you know, they really want more memory, and they really want it to be secure, and they really want it not to fail, and look to the future and be, but, you know, they just say, don't do anything, just give us more computers. And so John is able to navigate both the short term and the long term, which I think is totally awesome. And I think that's part of why MOC is in the mix. So let's make him welcome.
Thank you, Larry. Is this working? Yeah, that's working. So the first part of my talk is going to be directed at folks who are either suppliers or consumers that are considering participating in MOC Alliance. And then I'm going to talk about some of the research that we're doing with MOC that's of interest to 2 Sigma. But first, I'll tell you a little bit more about 2 Sigma We consider ourselves a financial services company or science company. We believe in the scientific method, applying that to financial markets, and we've been doing that since 2001 when we were founded. Taking advanced technology, data science, and applying that to algorithmic trading. That's how we make our customers money. Our businesses, our investment management, securities, which is our broker-dealer that participates in a lot of market-making activities. We also apply our work to things like insurance, real estate investing, private investments, a variety of things that are data intensive. So the history of our relationship is at the inception of the MOC Alliance. Larry, who introduced me, has been here since the beginning, has been working with Iran, and it's actually through a discussion that I had with Larry that led me to me being introduced to Iran. And we began with all of our security profile is such that we have been working on our own computers in our own data centers, and there was a very strong reluctance to moving to anything outside of our control, particularly to the public cloud. And when we started having discussions, prior to my getting there, when we started having discussions, there was a lot of angst about that. And those discussions led to the Amass Open Cloud to talk about what, in particular, were our security concerns. And as it turned out, there were a number of others that were interested, particularly Air Force, Lincoln Labs. We were concerned about both external and internal threats when using the cloud. And we were concerned about how do we appropriately assign the resources that you find in the cloud. And my participation with MOC is now focused on network attestation, improving the security of the pre-OS boot environment. So powering on the device to the handoff to the operating system. And that's what I'm going to talk about in a little bit. Now, in addition to infrastructure research, we also looked at ways to load data faster. That's a huge problem in the work that we do. When we talk about the data science that we do, eventually you have that data, you want to do some form of transform to produce a result, to make decisions. That led to work that we did for a project that was called Fridge Cache, not to be confused with the open source project Fridge, which is very similar, but different for some reason. E4N was something that was worked on here. I think it was your research, someone's research here. This led to work that another internal project called JAX that does a lot of cache optimization of data across our entire infrastructure. We also were looking at Python, making that a primary language for our development. Most of our work was always in Java. Python is now something that we use on a regular basis. And that led us to looking at Jupyter notebooks. And the challenge we had was we wanted something that would be more language agnostic, and that led us to develop a tool called BeakerX. And the MOC put us in touch with Red Hat, and they helped us move this more advanced, capable notebook, and helped us increase the community and build a community around the BeakerX and we open sourced it. So that was a huge benefit to us, to get others' perspectives to enable and grow this technology for us that we use heavily internally. And then lastly, we started working with Keyline back in 2017. There was interest there. One of my former colleagues at Two Sigma that's still working with us very closely started with Keyline, and now that interest is revived because we're looking for a network attestation server, which Keyline happens to be, something that we can use to work in this pre-OS boot environment. So the thing I wanted to talk about, just the mutual benefits that we receive from having this, the alliance, the word alliance, a union or an association for mutual benefit is something that comes into play very much here. We collaborate on a number of research topics simply through discussions. led us to this. I met Hugh Brock from Red Hat, George James from IBM. All these were introductions that were facilitated through this alliance that helped us explore the ideas that are actually coming, being developed into actual solutions that we're going to be using at Two Sigma. The other things that, in terms of this alliance, we use a lot of hardware on-prem. This hardware, when it is past its useful life for us, we actually donate all of the hardware to the MOC Alliance for their use, so it can continue to develop and benefit. And where we're going with this, the talk just before on the hybrid cloud, one of the issues that I'm dealing with in the firm, 10 years ago, we were worried about going to the public cloud. And now the problem that I'm dealing with is dealing with what I refer to as the faithful. These are the folks that think the cloud is meant for everything. And it's not. It's just another place where you can run your work. And what I'm trying to do is stop this pendulum that has swung and get us to focus on the ability to run our work in the place that makes the most sense. And focusing our development efforts where we can actually make better decisions across the infrastructure that's available to us, whether it be on-premise, off-premise, different clouds. This is an area that we're still debating, as opposed to just simply, we move everything to the cloud. The main thing that we need to see, and this is some of the things that I'm hearing today, you want to have a single operational plane across all of this infrastructure. You want to use the same security model. You want to have the same data presented to you across. You don't want something that's different. In managing, that creates the complexity that is otherwise wasting your time. So for us, our work actually is very amenable to making decisions at runtime where something runs, because we know what resources it requires, where the data may actually be. We can actually stage things. We just don't have the systems today that actually make those decisions. We take a very simplistic view to where data is. So this is where the work that we're doing, testing these things in the MOC Alliance, is where we have a greater opportunity to advance what's happening inside of Two Sigma. Because a lot of the things that we're doing inside of Two Sigma is very focused on our day-to-day. And thinking about these strategic changes to how we might operate is better suited to working or testing inside the MOC. So a little about our current work. So the person I mentioned earlier, Trammell Hudson, who used to work at the firm, runs consultancy, and a project that he started, SafeBoot, is something that we're very interested in. Not only for server devices, but also for our endpoint devices, the laptops that you have in your hand. So there are 5 goals. The main thing here is about running on a device that you trust. So the whole thing is about understanding how you measure that device, how you qualify its use for the purpose that you're assigning to it or expecting it to perform for you. So the things that we do in preparing these devices, we need to have an attestation server that's outside of the device. We want to boot only code that's authorized by our systems, and we want to run on devices that we trust. The main thing that we have left to do is to implement a robust attestation server. And one of the challenges that I have is within my own company again. I learned very early on in my career that when you dictate to your organization something to do, typically what happens is they find reasons to prevent you from doing the very thing that you're asking them to do. So the whole point here is to develop the testing, the results necessary to convince my own staff what is the right way, how we can run these environments in a different way that actually produces a better overall environment. Challenging our working of the systems when they boot introduces a very, very sensitive failure point. If a server comes up and it can't reach the attestation server, today that would mean that it would run. And so what we need to do is a lot of operational testing in a large-scale environment that we can't duplicate on our facilities. The MOC Alliance is going to be providing that kind of test bed for us so that we can actually show the inside operations, how it will adapt to this new attestation infrastructure. And we hope to actually apply that to the endpoint devices as well that may be disconnected. And that's going to be a very interesting challenge. What we're going to be doing in the next few months is developing the testing that we have for the software that we're going to be building. We're designing a protocol today, then we're going to be implementing that in a couple of months. We're hoping to leverage Keyline as a potential shortcut to getting this done. And with that, thank you for listening to my talk. If you have any questions,
John, we've talked some about safe boot already. Do you know what the current status is on getting that upstream, where Trammell is with it? I mean, we think this is really interesting. And I know it's a fair way out for something that we can commercialize and adopt, but it's really cool.
so safe boot, one of the key components is that it is a stripped down kernel that's going to measure the device for you. This is a kernel and an initRD, and that work is pretty much done at this point. We believe that that's production ready. Right now, the attestation server that we have implemented is simply the YAML database in front of a simple web server that's performing that task, but that's not something that's going to deal with a thundering herd, which I'm very much concerned with. I'm very focused on stable operation and making sure that we understand all of the failure points. I can't test all the failure points that I can contemplate, and I know we'll find new ones, and that's where the MOC Alliance comes in. That's where using their test bed and frankly having a ton of other people beat that thing, because I need to be able to show where it's going to break. I want to know all the failure points, and I can't use my staff to do that. We don't have the resources to do it. So safe boot as a product, we think is ready, and we're actually looking to employ that on the endpoints as well. So there's the end user devices, the laptops that you have, they're purpose-built devices. It's not a standard operating system build. We certify the hardware, we certify the operating system, and then we put bits on top of it. Competitive solutions are only things that are available to 3- and 4-letter agencies, and I don't qualify to buy them, so we have to roll our own. That's the level of the security profile that we have. So SafeBoot is improving both on the server side and the endpoint side, and that's where it came from. The SafeBoot was actually meant for the end user devices first. But this is what we're going to be doing going forward. And we're also, future thoughts are how we might apply that to cloud if there is a use case for it. Don't know yet. Okay, thank you very much.
We'll have another short break here. I know people were looking for their coffee. I believe it has arrived. So come on back here at 4:05 and we'll finish up our afternoon. Thank you.
Yeah, I need some coffee. Oh my gosh. Oh. I'm gonna go get coffee before all these other people get to.
electrical engineer and group leader for the embedded and communication systems for Draper Laboratory. William received his PhD in computer engineering from Northeastern University and an MS and BS in electrical engineering from Michigan State University and North Carolina A&T State University, respectively. Without further ado, please come
Thank you, Michael, for that introduction. Good afternoon, everyone. As Michael stated, my name is Will Tomlinson, and I'm the director of the Software and Application Innovation Lab, also known as SAIL. Before I get started, I do want to give thanks to the folks in the Mass Open Cloud Alliance, the folks in the Career Institute, and all of the other SAIL collaborators and participants today in this presentation for your time. It's greatly appreciated, and I'm happy to be a cherished collaborator within your ecosystem and happy to continue working together for future endeavors. So the point of this presentation is simply, as is entitled on the slide, to showcase the diversity of the domain research projects that exist that are deployed on the New England Research Cloud. From sales perspective, we will be providing, our PIs will be coming up here that we collaborate with to talk about their particular projects and the way that the software products they have help enable their research. And then we have our collaborator as well, Milson, on the hardware nerd side, giving a list of projects as well that also that are also deployed on NERC. So for today, the presenter, well, as a moderator, I'll be here guiding you all throughout the presentation. But from a PI perspective, we have Professor David Boas, who is a professor of biomedical engineering and electrical and computer engineering. Assistant Professor Naomi Caselli, who is in route, and she is assistant professor in Deaf Studies at Whitlock College. Professor Douglas Dinsmore, also in BME and EC and Klein, who's here as well, professor at Whitlock College in Teaching and Learning. And then again, Milson and myself will be guiding through the presentation. So essentially, every PI will be up here discussing what they talk about with day-to-day their research project, and specifically what the software product is that enables it. And then I will be here to answer any questions related to NERC itself and the deployment research that we're using to instantiate these products. So just a little summary before we get going. This slide is here just to capture the overall impact of NERC currently at the partner institutions. So 8 institutions, around 220 users, 55 PIs, and 60 unique projects span across the universities you see here on the slide before you. And as I mentioned, the first part of this is to talk about the software products that SAIL itself has developed that are deployed on NERC, and our PIs will be coming to give their own individual perspective of the research projects and the importance of the software that helps enable. So my first speaker is Professor David Boas, and he will talk about his particular application. Please welcome David.
Hi, thank you, Will. So I'm going to tell you how we've been interacting with SAIL for, about 16 months now, maybe 18 months. So my group has been developing this functional brain imaging technology called functional near-field spectroscopy for measuring brain function in humans. We've been doing that for a very long time. We've been promoting the development of the field. There's thousands of researchers around the world now using this technology. It's kind of like EEG in that you can wear it on your head, but EEG measures electrical activity of the brain. With functional near-field spectroscopy, we're actually measuring the hemodynamic activity of the brain, just very much like fMRI does. Maybe many of you have heard of magnetic resonance imaging. You can use that actually to image with very good resolution brain activity in humans as they're performing different tasks, but they're kind of doing those tasks in the bore of a magnet. It's not very natural, but with functional near-field spectroscopy, we're just putting light sources on the head and detectors, and we're able to measure brain function while people are walking around. So that's a vision we or many other people around the world are working towards. As the field has grown, and not just our field of functional near-field spectroscopy, but neuroimaging in general, and really just anything in the sciences, people are more and more aware of the need to share their data sets. And to share your data sets, you need standards for file formats and for data sets. And so we've been working with the broader community for the last 5 years to establish those standards So about 3 years ago, we finally released the data file format called SNRF for shared near-infrared spectroscopy format. And as soon as that was released 3 years ago, our colleagues started to adopt that into the brain imaging data structure format. So this is a specification for data sets, which tells you how to organize your data files into a hierarchical folder structure that is based on the subjects, sessions with that subject, data type, or an acquisition method. It was originally developed for MRI, extended to EEG, magnetoencephalography, positive emission tomography, and now FNIR is part of it. This is a very comprehensive specification for data sets in that there's a tremendous amount of metadata that is associated with the experiments. And you want to make sure you capture all of that metadata. So this bid structure ensures that the minimum required metadata is there in the data set. As such, it's rather complicated for a researcher to generate a data set which is compliant with this bid specification. So we set out to work with SAIL to create a cloud server, a web interface to essentially help users organize their data sets into a BIDS compliant structure. The idea is basically when you acquire brain imaging data, you get a data file in a SNRF format, and then we have this web interface that has come together quite nicely now, and it's in a closed beta release now. We're going to be opening it to the general public in a few months. But it basically allows users to upload their acquired data files into the appropriate subject folders. And it then creates all the metadata it can, extract it from that acquired data file, and then alerts the user to what metadata is missing, and asks them to fill in that data. So it's very useful to help you organize your data sets into that structure, which then is very useful if you want to share the data set with your colleagues in your lab. For instance, that is a funny experience we had at BU where helping 10 different labs across campus apply FNIRs to their various cognitive science or rehabilitative science experiments, and we told them, organize your data in this specific way. This was before BIDS. They came back to us and they've sent us data in 10 different ways, very annoying, which makes it very difficult to analyze data because it's not organized in a common way. So today, what we're doing now, because of this BF Cloud, we tell them, upload your data into the BF Cloud, and then we can help you analyze your data. And that's working very well. And more people around the world are starting to adopt this, and we expect it's going to grow quite well. And then, in the future, as we get more funding, serve as a platform for analyzing our data in the cloud. We can even imagine doing that globally. So that's why.
Thank you, David. Next up, we have Professor Hank Fine at the College of Wheelock, who's a professor of teaching and learning. Hank is a recent collaborator of ours, and his project is more at the infant stage, but we thought it was best because he has lofty visions, and we envisioned this project is to take similar heights that the FNIR's Cloud has today. We really want to have Hank come and talk to the large mass here to give his vision and talk about what his project and his proposed software product will bring to his research.
I think infant stage is probably a generous way of putting it. So I'm a behavioral scientist and see data science as a hobby right now. So I'm learning a lot, working with Will and getting to know Heidi and Brunpat, collaborators. Our goal is to ensure all kids learn how to read. It's not a small goal. If you're going to read papers, we have a crisis on our hands. About 1/3 of kids are not able to read at proficient standards by 3rd grade. Students living in poverty, students with disabilities, living at risk for disabilities. The statistics look abysmal. In Boston, I think you have about 8% chance of meeting 4th grade reading standards if you have a disability. So we have been working the last 20 years with a bunch of university researchers conducting reading research studies And so we have these huge data sets where we are actively trying to improve reading outcomes for kids with and at-risk disabilities. And these data sets are multimodal. We have learning data, behavioral data, neuroimaging data. Sometimes we have audio, video data, teachers teaching in the classrooms, students learning to read in the classroom. We're able to apply traditional statistics to see if we can improve outcomes for kids or not, or examine if what teachers are doing are actually influencing positive learning trajectories. But we have ideas that we might be able to gain some insights using machine learning and more advanced AI applications across these various data sets. And it turns out that that's not a software application that we have to date, to take multiple data sets, multimodal data sets, and be able to apply machine learning statistics and analytics to those data sets to gain some insights. So we have a working group with SAIL, and some Red Hat engineers are joining us soon to take these various data sets and be able to clean them, organize them in a standardized way, and then apply some machine learning analytics to gain some insights that maybe we weren't able to gain through traditional statistics. And we've been successful with one-off data sets. The game plan, the goal is to be able to offer this to other researchers who have other data sets so that they could access this as well. One of the areas that we've been researching is in kindergarten, when kids come to school, we don't have the technology to distinguish those kids who have a disability from those kids who just didn't have a high-quality, rich learning environment before they got to school. And so the educational service model that we've been developing and testing over the last 20 years, early intervention and prevention, the idea is if we give those kids evidence-based interventions and then they don't respond to those interventions, then those children may be candidates for comprehensive evaluations for learning disabilities. Response to intervention is the name of this approach. And so across all these data sets that we have, we're trying to examine, are there factors, teacher factors, neighborhood factors, student factors that predict as early as possible, maybe 6 weeks, 2 months into kindergarten, those kids that are going to most likely need the protections of special education and more supports and more services from those kids who probably just need some small group reading interventions for 1 year, perhaps, to catch them up to their peers. So that's really the goal, is to be able to get these various data sets and put them into a platform in the cloud so that we can gain insights to better support teachers, districts, administrators to identify kids earlier on so that we can support them to be successful readers. I'm not even going to go into our technical approach, but the idea is that we want to have an open side for scientists to be able to put their data into the platform, pose questions, gain insights, advance the field, and at the same time be able to provide direct services to teachers, parents, community agency members, and students themselves in a more intelligent way. And that's not a part of the Red Hat project, but it's one big project for us. Any questions? Or thank you very much.
Thank you, Hank. Moving on, our next speaker is Dinsmore. I usually make fun of him because he's a fellow Michigan native, but I'll leave him alone for today and give his talk as well.
So thanks, Will. Michigan native, so he went to Michigan State, and I went to University of Michigan. So there's really no comparison. I really shouldn't bring up Michigan. No. It's good to be able to come and chat with everyone. So I've got this idea for a project. So I'm into arcade games. Anyone who knows me, they're into arcade games. So what I'm going to do is I'm going to take pictures of the inside of my arcade games and wiring, maybe where the games are on, and do some thermal imaging of the board, and see the power they're consuming. So I'm trying to restore these and see if I can see, oh, this picture of the PCB, there's a part that's hot. And maybe that's the wrong chip. But I'm going to upload these to the internet and all that. But the thing that's holding me back from this really cool project is I have to boot a server up. I got to have computing resources in my house, a mainframe, etc. If I said that to you, you would say, Doug, that's silly. Why are you setting up that computing infrastructure in your house for that project? Why don't you use the cloud? Nobody, for the most part, when they want a website or some computationally heavy service, makes a mainframe, makes a large server farm. They use the services that this conference is talking about. But on the flip side, in biology, if I want to make it a drug, or I want to make a microbe that responds to toxins in the environment, or I want to make a new material from an engineered bacteria or yeast, I have to have a lab. There's no notion of sending that design experiment to the cloud. And so what I'm trying to do with my research here through an operation called the DAMP Lab, which stands for Design, Automation, Manufacturing Processes, is to make that cloud for biology. And the kinds of things we're trying to engineer are therapeutics, fuels, materials, sensors, and so that it democratizes the field, so that when any of you want to do that kind of biological resource, you don't need your server. You don't need your lab. How would we go about doing that? And so this is what this project is involved with. Because if you want to sit down and design an engineered microbe or a yeast or mammalian cell, what does the software look like? Do you say, I want an ATCG? Do you say, well, I just want to make it that if this bacteria comes in contact with heavy metals, it glows yellow? How do you do that? Well, one approach is to say, I want to build something, and I have a menu of services. So if I went to Taco Bell and I wanted to make some new recipe, I'd say, well, I want a tortilla, and I want some beans, I want to do it this way, I want guacamole. And you look at their menu, and you assemble the things you want to get the meal you want. So what the DAMP Lab is doing is providing 40 plus, more or less, microbiology services. So these are things related to DNA cloning, fluorescent assays, transcriptomics, basic storage and retrieval, liquid handling. We have a menu. And then you go to a software interface that SAIL is developing, and you literally drag and drop those services on a canvas, and you wire them together. And when you wire them together, it's implicitly creating a schedule that's going to be sent remotely to the lab, and it's the same lab here at BU that did all the COVID testing. So the DAMP Lab, for those of you who didn't know, has consumed or reabsorbed the same infrastructure that did 9,000 COVID tests a day for the campus. And so we're offering that capacity now to the entire BU community as a core facility. But again, the SAIL effort is to, again, expose these kinds of things. Transparency in the status of your job. It'd be no good if you sent something to the cloud for computing and it said, we'll get back to you when we feel like it. You don't want that in biology either. You want to say, well, here's the expected turnaround time, the quality, the parameters that I can expose to a user and that they can give to the lab. The kind of freedom. So again, the idea is that we have human technicians, just like that Taco Bell analogy. There's an assembly line of people who do things in a very standardized way, but we also have a series of liquid handling robots and automation equipment that carries this out. So again, the challenge to SAIL was what might that look like, how do they build that infrastructure? And it's ultimately powered by the traditional computing cloud. So when someone sends their job in, there's back-end processing, there's scheduling, there's resource allocation, all of those kinds of things. So again, you can imagine the front end kind of shown here on the left is this idea. You can kind of, you don't need to see the details, but you can roughly see, again, you have a canvas and you're dragging and stitching together services. And what you'd like to do is have that available for a variety of users. Power users will say, I'll double click on that, I'll go and I'll monkey around with the parameters, I'll set some things very specifically for that process to happen. But a more naive user might say, well, I just want this general thing, can you tell me what the parameters are? I'm going to say, well, the output of this cloning experiment which produces DNA, I want you to tell me if it works, what assays might tell you that it works, so we'll then propose those. You can imagine that the backend is going to be learning about the types of workflows people put together. You then go and put your data back there. It says this experiment worked, this one didn't. Eventually, if we do that enough, those become rules that prevent people from stitching things together. And then also for you that are not familiar with this area, you might be thinking, oh, they're engineering bacteria, they're engineering yeast, they're engineering mammalian cells. That sounds potentially tricky, both ethically and from a security standpoint. The other thing that happens in this flow is there's a security checking process. So we say who's making what, how's it being made. It goes about making sure all the biosecurity is in place. So again, what we're trying to enable is the same way you guys all think, well, I want to do some really cool computing. You never would think about booting up your own server farm. In the future, if you want to engineer biology, you would never think I need to have a lab. You would just go to the cloud, and this software will power that. So thanks to sales, it's been great working with everyone, and thanks again for listening.
Thank you, Doug. Next up, sorry, Assistant Professor Naomi Caselli, who has been a cell collaborator prior to me who joined Cell, so we want to welcome her to talk about her important work in her field and product that helps to bring it all together.
Thank you. I've been working with Cell for a couple of years now, so I don't know, 4 or 5 years at this point. Yeah, Naomi Caselli, I'm the co-director of the AI and Education Initiative, and I also run the new Center on Sign Language and Deaf Education. And the reason that I do the work that I do is because I care a lot about sign language and about deaf kids and deaf people. ASL, American Sign Language, was my first language along with English. We used it in my house because my dad was deaf, and I feel really lucky that I had access to 2 languages starting at the time that I was born, and was able to learn them and use them throughout my life and communicate and really connect with lots of people in lots of different ways. But it turns out that the way that I was really lucky, lots and lots of deaf people aren't so lucky. Deaf kids don't automatically have access to sign language, and deaf adults have to communicate through an interpreter a lot of times. Classes, other sorts of things aren't as accessible. And I think we've gotten to kind of an era where our capacity for computer vision and AI and natural language processing have put us on the precipice of maybe having technology that could augment some of that communication, could aid in translation, for example, or could make it possible to access your email through American Sign Language instead of having to do it through your second or third language, written English or another written language. The big reason that we don't have these technologies yet, and that sign language technologies really trail at this point, is not so much. I mean, there's plenty of open questions in terms of AI and ML, but one of the big reasons that we don't have these technologies is data. Having a large-scale data set of sign language that's labeled in a way that you can actually build a model around it is a not trivial challenge. It's easy to film lots and lots of sign language. I can run my camcorder or whatever. I've been able to do that for 20 years. I can do that for lots and lots of hours, but figuring out what exactly people are saying in a way that you can teach computers is much more challenging. And so I've been working with the folks at SAIL to try and develop infrastructure to make that possible. So we've one of the projects that we've been working on is SignLab, which is a software that lets you collect sign language data, rapidly segment that so you can find where each sign is starting and ending, and then tag those data in those signs so that we know in some reliable way what's being said. And that's been a challenge. American Sign Language and English aren't the same, so you can't just type an English label for every sign. You've got to, there are different signs that translate to different words. There's not always a one-to-one translation, same as for any languages. There's not, there's plenty of things that get lost in translation. And so what we've done is we've come up with a system that lets you use American Sign Language to label American Sign Language and kind of circumvent this problem. But that's required building some software to let you do that. and to label it. And with that, we've been able to create the biggest data set for American Sign Language to date. We are hopefully, we'll see if we get this application through, hoping to use what we've done around American Sign Language to extend these data sets to other sign languages around the world. Yes, there are other sign languages around the world. And we've been able to be really successful. We can get a model to recognize signs with 90% accuracy already, and we haven't even gotten all the way there yet. So that's one of the big projects that we're working on. The other one is actually the project that we started working on with SAIL 5-6 years ago, is on ways of making those data publicly accessible. So instead of just housing the data in a university where technologists have access to that data, we're trying to make it accessible to deaf people, to teachers, to students. And so we've done that through ASL Lex, which is a lexical database for ASL that's got an interactive visualization that lets you explore the American Sign Language lexicon. You can find that if you Google it. You can see ASL Lex, which the SAIL folks helped us build. It's an award-winning visualization. We won the Popular Science Busies Award for our visualization work there, and people use it a lot. ASL learners, people who want to know a little bit more about ASL, it's a way for you to kind of browse it and learn all about it. And yeah, thanks to SAIL for really supporting us through and making that possible for the past several years.
Before I pass it on to my colleague, Wilson, just want to reiterate that these are software products that we envision being maintained on this production cloud environment indefinitely, essentially. These are right lock in step with the traits we're observing from SAIL, our vantage point, in that the research products coming from PIs are no longer just the 2 for 3 months and simply wrap up a study and conclude and go home. These things are designed to scale and have users and features over time, and really having a production cloud with the flexibility to meet those needs is a very important thing, and we're thankful for the folks who have helped orchestrate NERC and the things that's brought to bear so far to help with these goals, and we look forward to what is to come over the horizon. This is a snapshot of what we have at SAIL in terms of resources currently in NERC. I mean, we've been transitioning workloads over like less than a year already, so things are slowly being pushed onto this as projects come into our ecosystem. We are naturally pushed into this platform as well. We envision these numbers that you see here growing and scaling even over the next few months based on our trajectory here. A couple other notable projects I have here listed. One is through the public-private partnership with the Mayor's Office and the Boston Women Workforce Council, which is essentially a data collection tool that leverages multi-party computation to help to obfuscate the centers of the data, but help to measure the gender and racial wage gaps collectively across the greater Boston area. We have our own authentication microservice. We have a suite of microservices that we're developing that are to put on NERC, but our authentication service was the first to be dropped on NERC. And then we work with Framingham Heart Study on a number of different projects, but right now, the most notable is a proposal assessment system for a particular type of research proposals that they ingest in their platform to help co-assign and to grade and to deliberate on the result to provide funding to this agency. So just to wrap up, that this is a very important project, not only to their own research fields, not only to SAIL, to the community as a whole, and we hope to continue to have the resources to maintain them for years to come. I'm going to pass to my colleague Wilson, who's going to give a similar flavor of talks, but with Bentley, Harvard, and Northeastern projects at the forefront.
Thanks, Will, and thanks, everybody. So I'm here to present some of the interesting use cases that are using NERC, especially from Bentley, Harvard, and Northeastern. So I'm presenting those PI and the collaborators. So the first project is titled NIS Funding Drop in Meta-Analysis. So this is from Edward, Matthew, and Fred. They are trying to create a dashboard that allows users to search for drops and biological elements. So this provides a year-by-year detailed breakdown of NIS funded grants from year 1999 to 2020. And this tool offers insightful information for the funding patterns for the dog research. And the breakdown is done on the basic research as well as on the applied research. So the grants are categorized by the government institutions as well as grant criteria. So this is very important for the researchers to get the insight and also export those data for their research also as well as for the collaborations. So the dashboards provides the useful insights for the researcher, grant writers as well as policymakers. The interface looks like this, where we can see the drugs as well as their biological targets and the corresponding visualizations dashboards. So another project is titled Newspaper Database Project. This is from Professor James Snyder and Mitchell from Harvard University. So the main challenge of this project is to design a database that is robust and also store large amount of storage, and also support for full text searching with high accuracy as well as high speed. So we suggest them to use Elasticsearch, and most of the time, considerable amount of time is spent to scrape those data from US Library of Congress as well as uploading them to the Elasticsearch. So also they optimize the search time by providing the search keywords so that those keywords are not too narrow, that will not miss any important data, as well as not too broad so that they will not select any redundant or irrelevant data. So on NERC side, they are using two Ubuntu powerful machines. One is for the main deployment and another is for the testing. So they are using around 4.5 terabytes of storage for storing all those data from the newspapers. And also we provide the technical support for them to host those servers as well as the Elasticsearch database. So the main primary outcome of this research is the development of the highly scalable database and also uploading those data from there. And also substantial amount of time is spent on curating and continually uploading those data on the database, on the external source. And they are also developing a framework to extract a subset of the database that are leaning towards some political views and also trying to test them with several keywords to search on. So future work, they want to use this political subset of data set and then perform some classification tasks and also label those data so that they can perform some natural language processing as a truth or baseline. So another project is titled Particle Flow Code 2D. It's a PFC 2D version 7 model. And this is from John Saw, Andreas Place, and Christine Chiaima from Harvard University. So the main objective of this project is to understanding of the ground surface observed during large earthquakes. So the approach they implement is combining the studies of post-seismic ground surface structures and analog sandbox fault experiment to inform geomechanical models. And they implement the method called DEM, so it's a distinct element method. And their finding is a parameter that affects the ground deformation characteristics like depth, height, width. And also they found out the key parameters influencing the scrap morphologies. And the key finding of this research is the localized fault scraps are prominent in strong sediment on steeply deepening faults, whereas broader deformation is prominent in weaker sediment on shallow deepening faults. So out of this, they propose a fault scrap classification system, and this model can be used for deterministic and probabilistic assessment in fault displacement hazard analysis, FDLG. And they found out DEM is a suitable method for model geologic processes of faulting and granular mechanics of soils and sediment deformation in the shallow subsurface. So the future of this kind of research can be used in earthquake hazard analysis and mitigation so that we can minimize the loss of lives and also damage of structures. So on the north side, they are using 80 trials to run on NERC. They need operating system, both Windows as well as Linux. And each trial takes around 5 to 9 hours, and each trial generates 5.6 to 11.2 GB of data. So they opted with GPU A102. That's a GPU favors that is available on NERC with 24 cores and 192 GB of RAMs. And they found out that each trial requires like 40% of the CPU and 45% of the RAM from the machine. So they can run 2 parallel trials in the machine at the same time. And another project is titled Functional Annotation of Variants Online Research. It's favored and also variant annotator for large whole genome sequencing studies, favored annotator. So this is from Hugh Feng and other team members from John Bean Lab, and they are trying to achieve these goals. Like they want to design a database that has a data from whole genome sequencing, and that consists of data around 32 terabytes. And also they want to have a web portal that queries those data. And also have a scalable annotator on top of it. And they have implementation on different cloud-native platforms like NERC and Alert. So the main use case of favors are functionally annotate large whole genome sequence studies and also facilitate rare variant association studies. So they choose Favor as the backend database that is based on Postgres because this is easily available to integrate other existing databases. And they have around 8.89 billions of total variants, and that includes 15 annotations in 13 categories, and also a wide range of integrated scores. And beside that, it supports the indexing so that we can do quick single variant or region and gene variant label annotation queries, and also provides the summarized statistics. So this diagram shows the high-level view of this project. And as I said, they need a database and the querying online web portal, and also the scalable annotator that can query on single variant as well as region and gene level variants. So currently they are using Google Cloud, and the interface looks like this, but they already migrated it into NERC with the modern and user-friendly interface. And they already found out that this is increasing the response time on NERC rather than using the Google Cloud. So another project is titled Enabling Geospatial Research using High Performance Computing from Wenyi Wang and David Cocker from CCA Group at Harvard. So this group supports the research and teaching across all disciplines in the Harvard that are related to the geospatial technologies and methods. So primarily they focus on analyzing the big data on geospatial field. So they support those tools and methods and also develop them. And also they provide the resource required to scale them so that they can process those big data. And beside that, they also develop and design platforms that supports to visualize those big data processing. So this Billion Object platform is already hosted on NERC, and this has around like 1 billion geotags geotagged tweets, and also they implement sentiment analysis using natural language processing model. As they already have the geographic enhanced data, so they can use that data set to develop some user interfaces and dashboard for analysis. So this shows the output of this project, like it's showing. So user can filter the data using different keywords. For example, they can search on the tweets text, like they can search for climate. And this will allow not just searching for keywords, but also they can search on space and time. So you can see the response time for this amount of data is quite fast because the backend infrastructure used on this project is more like GPU compute-based infrastructure. You can see they can search on a range of date, and that will narrow down the search results. As well as they can search on a specific locations, like we can search for Boston, how many tweets are talking about climate. So you can see this narrow down the search rates. So this kind of infrastructure is quite powerful because it's super fast and also more user scalable. So this kind of data set can also be used on other use cases like climate change and impact on psychological well-being, as well as global sentiment analysis during the COVID-19 lockdown. So those are two use cases. Some of the publication out of NERC resource is from Arjun Gua and his team from Northeastern University. So the first paper they published is titled "Do Machine Learning Models Produce Type Script that are Adapt Type Check?" So we know type inference is a key problem in programming languages, and there are some projects that try to solve this problem by using machine learning. But this paper tried to present the limitation of the existing approach and try to address them in time uniform manner. So they use NERC. For this, they need GPU-based virtual machines. So they use A100 GPU nodes to evaluate those performance. And also, interestingly, this kind of infrastructure is helpful for the reviewers so that they can access them as well as they can evaluate the research work. So the reviewer from ECOP is a European Conference on Object-Oriented Programming. They are able to access those resources on NERC and then evaluate the work published in this paper. So another project is titled Big Code, Responsible Neural Code Generation Models. So this is a collaboration between industry and Northeastern, especially from Hugging Face, ServiceNow Research, and Northeastern. So Big Code is an open source scientific collaboration tool that is responsible for development of many language models for code, as well as empowering machine learning tools. And Northeastern is the key lead on this to evaluate the performance of this Big Code, and they using NERC to evaluate those performance, using some compute resource as well as the GPU resources. And this paper has published and also received the Best Award at the Deep Learning for Code DL4C workshop. Yeah. So these are some of the great use cases that are using NERC, and so you can think about having on-premise cloud services for any research need, and we provide all the cloud-native infrastructure as well as storage and compute resources for your research. Yeah, so if you have any questions.
All right, now it's on. So my question is very simple. What is the biggest hurdle, now that we've done this for a little bit, from a researcher wants access to the system, so they're productive and they're doing research? What do you feel like this, like, when you engage with them like Nelson and others in SAIL, and you're doing that engagement, what is that thing that you're doing that helps them?
Yeah. So the main hurdle is like, they know the problem and they don't know like how can they solve those problems, right? So we can offer them the technical expertise and also give them the solution, like architecting the problem. For example, in this problem on the database project, they don't know, they have the data, but they don't know about like how can they store that kind of variations of data. So we can support them like giving some technical suggestions, like on the technical aspect of the problem, and then yeah, supporting those, because resources on NERD can be reused and used for that purposes.
I just wanted to add one more piece to that. I think, so from sales perspective, one thing that we need to talk about is the management of bugs and troubleshooting software that comes out when it's already in production. So I think another element to add is that you said we've instantiated our own method of having CI/CD pipelines that facilitate rapid updates to code that's already deployed on there. I think that from a once it's operationalized standpoint, being able to maintain operation in a more seamless fashion, that's the thing that we've added as a piece.
Follow up on that. Do you teach the researchers those CI and software engineering methods then?
So not the researchers per se as a PI, but we at SAIL offer that software best practice consulting to students and students within their lab as well as an option. And so it goes to that sense of being able to maintain the software over time. SAIL is sort of the foundation unit here, is that we try to maintain that competency and that knowledge base such that as students, undergrad, graduate, postdocs transition, then someone has institutional knowledge to maintain it.
So earlier today, the Massachusetts political group said that they initiated having NERC come into existence or all of this research. How does the New England version of cloud computing for academia compare to other countries like California or Europe?
Yeah, so like we have on-prem industry level cloud services provider. So people, like if you think about having cost saving and more responsive cloud setup, then rather than going to others, you can opt it for New England versus cloud. So like I showed on some of the use cases, people are still evaluating the performance on public cloud versus using on private cloud. So they are already seeing some substantial change on the response time, as well as the cost will be very minimal on the.
So I have a question for the DAMP lab. So how would I think differently about this infrastructure regarding intellectual property? I'm trying to get my head around using a public cloud with IT resources, using programming. So you're dealing with physical things, I believe. So how do you protect? I don't know that you have a level of abstraction that could hide the idea sufficiently to prevent any kind of theft.
Yeah, so that's a good question. So on some level, you could make the case that if you're a biological manufacturing entity, the end result is just the sequence. So if that sequence is your secret sauce, that makes that protein that you really want protected, how might you you want to make sure that's secure. So for folks that have strong IP concerns about the actual DNA sequence, some of those things we end up partnering more intimately with them as a manufacturing facility. So as a core facility, they come, they may not go through that same interface. They may say, we want to partner, we have to put an IP agreement in place with the university. Those folks are relatively rare. So most of the folks, just like their IP is actually how they're going to be using it once they get the information from us. They're going to get something, they're then going to take that, engineer it, maybe put it together with something they have at their own facility, put that into a host organism, they're going to boot that up differently. So in the case that it does matter, we work with them more closely. Many people don't care. And there are some things that I think are just basic computational infrastructure security things that are just completely computer science, about how we encrypt things, how we have a secure database, how we do those. And that's where SAIL can really be helpful. That we can minimally say that the infrastructure is as secure as industry standard. So those things are helpful, because they know now it's not me running something in my lab. So they feel safe about those things. The other point, and I don't want to talk too long, is this idea about material transfer. So you do get something and you have to send it to someone. How do we make sure that's secure? That's an entirely different discussion about how we do material transfer agreements, but we're working on how to make those also robust and who we're sending things to. It's a whole good discussion though.
Any more questions? All right, well, thank you, folks. I'll turn it back over to
So, hi, my name is Michael Dainsman. I'm the Director of Engineering and Product at MOC Alliance. I get to do something really fun today, but also a little bit scary. I get to thank a lot of the people who are working as a team to make all of this stuff happen. And the scary part is, you saw that list that Ron flowed by very quickly earlier. I'm quite certain I'm going to miss people, and I apologize for that. Ron and Peter spoke about how we got here. And we heard from some people doing fundamental research that's leading to new products and software being pushed upstream. We also just heard about a group of really cool products and projects that are going on the NERC. And they're really cool things. Wayne and Scott spoke this morning about the complexity of fitting cloud offerings into existing business systems. And that's something that is really kind of non-obvious. The HPC systems, the research IT groups, have these existing systems that they use to bring people on board. And we needed to take a cloud infrastructure for OpenStack and for OpenShift, and we had to make that actually fit into those existing systems. And I want to just talk a little bit about that, but I wanted to quickly show you these slides just to refresh your memory about what some of those things were. There was access and resource management. There was user support and service monitoring. There was reporting and accounting. There's the storage, which is a huge separate project. It's a giant multi-petabyte data lake that we rely on. One of the things that we've worked on incredibly hard since we all were last together in 2020 was, how do we create one team? How do we take these different organizations and these different groups within organizations and work together as a team? And maybe even more importantly, how do we create ways of working that allow us to have overlapping meetings for the things that we're working on together, but also make sure that the groups that are doing other things separate from that, because let's face it, this is a busy group of software developers and the like. How do we make sure that we're doing coordinated planning? What's the best way to use Slack? when you're going between different organizations. These are the sorts of things that seem like they should be really simple. But I'm seeing some heads nodding in the office, nodding on the floor going, yeah, that's not simple. So I really just wanted to call that out. We owe a debt of gratitude to a really long list of people, and I know I'm not going to get to all of them here, but I wanted to take a couple of minutes and talk a little bit about them. So there's a group at Northeastern working on FPGAs. There's a group within the BU Research IT organization. There's a group of people at UMass. There's a group of people that are part of the core team at the MOC Alliance. There's a group at Harvard University FASRC. There's a group of folks working with us from Red Hat, from the CTO's office, as well as from other groups within Red Hat. And there's the MGH-PCC, which, frankly, without it, none of this would really be able to fly the way it does. And so I'm going to attempt to go back to 2020 for a second. I decided I wouldn't show that old slide that had a lot of these same folks. I had less white hair then. Back in 2020, the cloud offerings we showed, we had a version of this slide. At that point, we were running a Kaizen OpenStack. We were running OpenShift clusters. We were beginning to be able to run some Power 9 OpenShift clusters. We had some bare metal servers. We had some OpenCloud testbed. We had a bunch of Ceph storage. We had some Ceph storage research. All of that was being run by essentially 4 or 5 software developers. So I want to quickly introduce, or in some cases reintroduce, some of those folks. Nancy, who some of you met earlier, or all of you met earlier today, is our new managing director. And this time next year when we're meeting and we're talking about the fact that the services being offered have become self-sufficient, it's going to be in no small part due to her efforts to sort of corral a bunch of really hard problems that seem obvious, but in the world of academia are really complex, into a thing that we're going to be able to charge folks for. Another person I want to call out, who you've seen very calmly walking around today, is Tara Moran. Her title includes the word coordinator, but that completely overlooks the concept of special projects. This is a special project. Anything that went well today was because of her hard work. And anything that didn't go well, that was probably me. So, Ken Rudolph is the gentleman you see running around taking pictures. He's a very talented graphic designer. He helps ensure that the messages that we intend to convey are actually what we do convey. And I should note that this page would never have made it past Ken. You didn't get to see this before. He's also been helping to organize this workshop. Sophia Monkman is the director of corporate relations and has been instrumental in coordinating our relationship with our corporate partners, but also our relationships with our university partners. There are some groups I'm going to mention very briefly, but not in detail. There are some really brilliant folks in the BU Office of General Counsel who basically take these crazy visions that all of us come up with and figure out how to put in place agreements that allow us to actually make those crazy visions reality. And they do so with good humor and patience, even when we are really asking for stuff that nobody's thought of before. The staff at the Hariri Institute of Computing and Computational Science and Engineering, or Hariri Institute as we like to call it, they provide guidance, they provide assistance, they've been helping run the workshop today. They allow us to have a much larger impact than we could possibly have otherwise. And I want to talk a little bit about some of the folks right up there at the top who are the core engineers. When I started this, I was basically duplicating a slide that we did in 2020.
we've been really lucky because we've had a lot of continuity in the core engineering team. I'm not going to cover all the areas that this group works on, but I'm going to cover some of them. Christy helped stand up our first OpenStack cluster while he was a student, and he's been an active participant in the Open Infrastructure Foundation, the technical committee there, as well as a technical lead for a work group there. My brain just went blank, and he's going to give me grief later because my brain went blank. I should have put it in here. He's worked closely with members from Harvard BU and the MGHPCC to help implement the federated authentication for the MGHPC and NERC, which was spoken about earlier today. Naved worked on the initial implementations of Hill and BMI as well as ESI. He manages our networks and hardware, as well as having stood up monitoring back when we were like, monitoring? Yeah, we should probably do that. Robert maintained our early OpenShift clusters and has been working on integrating the NERC production cloud with XD mods so that we can actually implement the cloud cost model that we've been talking about. Lars, while employed by Red Hat, has been an integral member of our team. He's provided technical guidance, frankly, on everything that we work on. And we're very grateful to all of those folks who've been with us for a number of years. Akan joined us as a part-time employee while a UMass undergraduate, and he was very focused at that point on the Open Cloud testbed. More recently, he's become a full-time employee while finishing his master's degree. And he's been working on, among other things, a proposal defining how a central ESI network would actually work. And in his spare time, he's been coordinating the intake of the over 1,800 servers that were donated by Wayfair. Kim joined us a bit over a year ago as a technical project manager. He's helped ensure coordination across the different organizations working on the MOC Alliance projects. He's researched, proposed, and implemented improvements to our development process, and generally kept us moving in the right in the right direction with both grace and good humor. There's a group of people, some of whom on here, I challenge you to find busier calendars. Meet every week pretty much, or every other week in some cases. You've heard from all of them today, but I just wanted to call them out and thank them because there's just no way that we'd be where we are at without their help and participation. So that would be, I'll quickly say their names. Orban, who you've met, Wayne Gilmore, who's in the back of the room, Scott Yokel, Heidi Dempsey from Red Hat, Nancy Clinton, and myself, although honestly my calendar's nothing like theirs. So there's this much larger team, and I want to talk a tiny bit about that. As I mentioned earlier, since 2020 we've been working really hard, and I'm going to have to speak up. We've been working really hard to work as a single team focused on the priorities that are identified by that operational team. Recently, one of those has been the NERC. That initial development team consisted of Justin Riley from Harvard and Augustine Avaris from BU. Over time, they also were joined by Nilsson, who you got to see a few moments ago. But also over time, James Colbert from the MGHPC became involved. A group of software engineers from the Red Hat CTO's office became involved. Some contractors from Red Hat helped us to figure out things like scaling issues around OpenStack and OpenShift. The MOC core team was involved. And throughout all of that, Justin and Augustine took on all these additional folks with grace and good humor and welcomed us into Slack rooms. And I knew that we had finally hit the point where we were working as one team when two engineers from two different groups growled at each other in Slack. And I thought, yeah, we're a team now. We're growling at each other in Slack. And then they both sort of said, oops, sorry, didn't mean to do that. But that's kind of what it took. Wayne and Scott told us at the beginning, the people part of this is going to be really hard to do. You don't realize that it's harder than you think. And they were absolutely right. But that group of people who they pulled together initially And the group of people who came to work with us on this project made it so much easier, and we're very grateful. All of those people, from Justin and Augustine to Milan, who manages NIST, to Nick, who's a network architect at Harvard, folks who we work with on an as-needed basis at different stages of the project, have just been a joy to work with. And it's been a proof of concept for us of something that we set out to achieve, which is how do we take software development organizations from different cultural groups, and by that I mean every company has a different culture, frankly, in each company, every dev team has its own culture. How do we put them together and work together as a team? And if you take away one thing from this talk, other than, hey, there's a lot of really cool people working on this project, I want it to be that we think we have a model that is heading us in the right direction, and we really, really love more of you to become involved. So, what else is going on today? Well, hopefully you all have found some good restaurants. There's lots of them around. There is one more, as of this morning, there may have been others added, I haven't looked recently. There is one more Birds of a Feather in room 310, and it is can the MSC be the new version of the Library of Alexandria, and how to make it, sorry, that should be how, and how to make it fireproof. And unless there are other questions, this is what we're up to for tomorrow.